Let's see if we find out. Okay, let's see if we find out. With you and Bob, everybody was.
Yeah, we are good to go.
Okay.
Yes.
Everybody, please keep it down. I'm trying to do a sound check with the other regions. We're coordinating. Thank you. Bob, are you there? All right, well, can't hear you, but we'll start. Here we go. Well, welcome contestants, coaches, volunteers, distinguished guests to the 2023 ICPC Regional Eastern Contest Eastern Style. This year's contest is our most ambitious yet. We're running the 3 Eastern contests concurrently. Many of the problems will be the same, but not all. We have top-notch guest speakers along with ICPC Live recording all the action. So that being said, let me introduce you to the Eastern Regional Contest Directors. The Northeast RCD, Dr. Ivana Bezakova. The East Central RCD is Dr. Bob Kramer. And I'm Greater New York RCD, and my name is Joe Terlizzi. So Ivana, you'd like to say a few words of welcome at this point?
Absolutely. Thank you, Joe. Hello, everybody. It's wonderful to see you all here. I'm Ivana Bezakova. I'm the Regional Contest Director for the Northeast North America region, and we're excited to partner this year with Greater New York and East Central. This contest wouldn't be possible without many people behind the scenes. We would love to thank our judges. We would love to thank our regional contest directors, their deputies, also all site directors and the teams behind the contest. Good luck to all, and have fun.
Thanks, Ivana. Bob, you want to add anything?
Hey, welcome everybody. I'm Bob Kramer, the East Central Regional Director. I would also like to thank you all for coming out. Here in Youngstown, it's a dreary, wet day, but typical for our time of year. The leaves look very beautiful outside. Again, as Ivana said, this is not possible without a lot of help behind the scenes. So yeah, thank you. A big shout out to all of the judges, the site directors, all of the volunteers. There's a lot of volunteers that help out. And also, I'd like a big shout out to the coaches who put in a lot of time working with the students, training them, getting them ready. So thank you all. Thanks to Bill and Lydia and all the ICPC staff who helped coordinate all of this over the years. As Ivana said, have fun, enjoy the time. It's a lot of fun. I remember my days as a contestant a long time ago. It's a really great experience. So enjoy, do well, good luck, have a safe trip back home afterwards, and back to Joe.
Bob, I too would like to thank all our volunteers, including the coaches that work countless hours to make this possible, and of course all our host sites that provide the facilities to make this happen. But enough for me. So to deliver our keynote speech, I would like to welcome the man who invented and developed C++ programming language, among other countless accomplishments. He's currently a professor of, currently a professor of computer science here at Columbia University. And I apologize for the misspelled solution of the name. I listened to that name file on your website over and over again. Dr. John Strusko.
Okay, I cooked up some slides here this morning. And mostly pictures. The question is, can we get in to actually use them? That sounds good. Sounds good. Yeah.
Technically, but I'll try to fix it. Sorry, I can fix it.
Got it? Yeah. Let's take a conversation. Slides. Oh, I can do it. Okay, that actually worked. We should have done that before, of course. But when I came to the university today, the engineering entrance was closed and I had to walk all the way along to get here. Anyway, I was asked to talk a little bit about the evolution of C++ and if possible say something inspiring. I don't know how to inspire or preach, but I can tell you a little bit about C++. Any good language, any good project starts with a problem. Dennis Ritchie says there's languages designed to solve a problem, as there's languages designed to prove a point. There was no doubt which one Dennis wanted. And I'm definitely on his team. So I decided back in the dark ages to build a distributed Unix. And if I'd gotten around to doing it, it would have been the first Unix cluster by a decade or two. But I couldn't do it for a variety of reasons. The one I picked on was the fact that I didn't have a language that could do what I wanted. I needed to do really low-level, grubby, machine-close programming, device drivers, process schedulers, memory managers. And then I needed to do the high-level stuff, because if two parts of the system runs either here or there, you have to formalize what it is that runs here and there. And you can't have a rat's nest of pointers and bytes and things like that. You have to have a proper interface, you have to have a communication channel. And no language could do both. C and another couple of dozen languages could do the third. Singular could do the second. So I got the idea of just taking the object-oriented features from Singular, where they were invented, and put them into C. Fortunately, nobody told me it was impossible, because everybody knew that. And since I was young and naive, and didn't know it was impossible, I did it. You cannot do things like that at a scale by yourself. There's a lot of, especially very smart young programmers that think that code is everything and they can do it all themselves. That doesn't scale. You have to be part of a community where you can share what you're doing and you can learn from the others. Mine was, among other things, Bell Labs over New Jersey. If you haven't been there, see their museum. Anyway, so over here we have the physicists, and they do things like inventing fiber optic cables and the charge coupled devices that drives our cameras, things like that.
Sorry.
And on the other side here, the software guys, C, C++, Unix, R, things like that. Very rich area, rich in technical problems. We're just running the communication systems for North America, all of it. And there was rich technical culture. If you had a problem, well,
Okay.
and I give them the finger. If there was a problem you couldn't solve, there was always a toilet somewhere down the corridor. And you could walk in there because the culture was you only closed your door if there was something really unusual going on, like a management meeting or something like that. All the doors were open. And those great people, there's some people you can see there, some you've heard of. You may not have heard of Doug McElroy, but he was a smart guy that we all went to when we got stuck. That includes Ken Thompson and Ben Richard, that and me, of course. If you then want to look what C++ is, it started as the direct map to hardware, initially from C, zero overhead abstraction to get away from the hardware, because programming hardware can be fun, but it's not very productive, and it's low level, it's error prone, all of that, so you need to abstract. And so you get the fundamental data types, the memory model and such from C, that got improved a few years ago for C++, because world had changed and C has adopted the C++ memory model. But basically, we need to deal with hardware, whatever the hardware is now. And zero overhead abstraction, we have to be more elegant, more powerful, and make sure that it all works fast enough. So all good engineering relies on feedback. That is, you can't just sit down and build the perfect language. For starters, you don't know what perfect means. And anyway, by the time you have finished it, the world's idea has changed. So C++ had to evolve to meet the needs. I knew that when I started. I was just one guy writing a language. I didn't even in the beginning know about writing a language or about building a tool. But I soon realized that building the perfect language was a non-starter. You build something the best you can, then you see it how it works. You listen to the users, you see what problems they have, and then you make it better. And the decisions have to be driven by real world problems. Yeah, theory is great when you know what the problem is, but theory is not a good guide for what the problem is. So you work from there. And C++ actually did evolve over the years. We've been in this business for 4 decades now. And well, it's not your father's C++ anymore, unless you're one of my kids. Anyway, started down there, one user, and it's inaccurate. I've had a couple of users that work. And we have all of these features, and they have to fit together. The hardest part of language design, the hardest part of all large system design, is to make sure that the bits fit together, so that you don't replicate things all over the place, and that you can use things in combination. That's hard. That's what I spent most of my time. So also stability is essential. I saw somebody today saying longevity isn't an aim. Of course it's an aim. If you build a system today, you want to run it in 10 years if you are an organization that has 10-year projects, or 20 years projects, or 30 years projects. That's the Large Hadron Collider at CERN. The original software for it was designed and written maybe 25 years ago. It's still running. You can't just replace a big system easily. There's technically difficulties, because usually the reason you want to make major changes is that there's something new that has to be done. The old version has to run till the new one is ready. If it takes 5 years to build a whole new infrastructure, tens of millions of lines of code or hundreds of millions of lines of code, you have 2 teams running. They both cost money. It's not all free. And they don't communicate very well unless they have a shared set of tool chains, shared set of ideas. And basically, when you look at Gall's laws, there's a complex system that works. Invariably, it's found to have evolved from a simple system that works. That is also part of the engineering thing. You see what works and what doesn't, you fix. What works, you strengthen. Okay, so the foundations of C++ today is not that different from when we came out of the 80s, where I had articulated the ideals and knew roughly what I was doing. There's a static type system, equal support for built-in types and user-defined types, low-level, high-level code, value and reference semantics. Value semantics is what makes it hard and makes it nice to write a piece of code. It's easier, it's simpler and easier to optimize, but sometimes you have to fiddle with pointers and bytes and memory things to make those abstractions work. So we need both. Systematic and general resource management, scope-based constructor, destructor stuff. Constructor, destructor came in the first week or two of the design of sealed passes back in 1979. It was one of the things I really wanted that grew into general resource management, operating with error handling. It's called RAII. I never was good at naming things. Efficient object-oriented programming, of course. I came from Simula. Flexible and efficient generic programming. I just wanted it. This is where we have the templates and concepts and all this good stuff. And compile time programming. If you can calculate the answer at compile time, it beats most things you could do at runtime. I mean, simply reading the answer out of memory, well, it can take time, with caches, but still, it tends to beat computing it. And direct use of machine and operating system resources. We don't want interfaces that imposes amazing overheads on things. And so, one thing I'll get back to here is the community. When we are writing code, it's only part of the picture. It's a central part to write code. But to have these people that discuss things as if having one particular language feature or being able to write a formula slightly simpler is the essence of programming. Well, to build a real system, there's so many parts of it. The language is a central part, but we don't want to degenerate into mere hacking. We have standards, we have the communities, people have meetings, people talk, people have groups on the web, they exchange articles, people do research in them. Industrial use is important. It sometimes doesn't reach through to academia because people who are building interesting systems tend to be too busy to start talking on Reddit or something like that. Research, of course, libraries. I mean, writing anything in the base language is a pain in the neck. In any language, for just about anything, you need libraries. On the other hand, with a good library, just about anything can become simple. And we do that. Tools, I want more tools, especially static analysis tools. I've been saying this for ages, and it's not coming as fast as I want to. And then there's teaching. Many years ago, Arno Penches, who was head of Bell Labs at the time, he got the Nobel Prize for the background radiation, was trying to explain to a couple of hundred managers why you needed teaching, why you needed training. He says, well, you take an old tool, you take a saw, you know how to use it. Now you get a new tool, a power saw. And if you use it the same way as you use the old one, so basically any language, any feature, any library needs to come with a guide for how to use it. So teaching is important, and quite often teachers like to teach old stuff or simple stuff. It may not always be the right thing, but we need to work on that. And so basically, for me, some of this worked. So I'll show you some pictures. It's talked bigger than I can do it. So these are applications of C++. I'll point out that one there with the guys in the white suits. That's the kind of machine that makes all of our high-end chips. Okay, so if you wonder where C++ is, the answer is, do you have a high-performance processor? If the answer is yes, you don't have to talk further. The others also have. And good software is invisible. Most of what you see here, you don't see. You just use it. That gadget there, the box, it's around industrial scale around. You go to your dentist, they know scanning these days, server farms, and a lot of locals just to show off a little bit. There's the JavaScript engine, the implementation of the various languages, including Java. Okay, I will stop, and maybe there's time for a question or two. I promise to speak fast.
You have a question? Speak up. This is your one chance. Yes.
I had a question on, before when you mentioned like compile time programming, like RT++, is that a function of the language or the function of the compiler?
Oh, the main way of doing compile time programming in C++ is just to stick the keyword context in front of a function. That tells the compiler that that function is not supposed to have side effects. You can't read global variables, say, and you can't write outside your scope because it hasn't started yet. You're in the compiler. And any language that can do that can do some of the things we're doing. The point is that most other languages haven't made it a priority and hasn't put it into industrial use, and you don't find it in your hash codes and things like that. So it's a compiler's job, but only once you've made the language so that it's possible. Most of the functional languages could do it.
Just a random question. Most languages are written for one moment architecture, right?
Sorry?
All languages are written for one moment architecture for CPUs, right?
All languages are written for von Neumann architectures. Well, for some definition of von Neumann architecture, yes, except for the ones for quantum computers. Von Neumann architectures also include multiprocessing, and all the languages today takes care of that. And so you have to think of things that von Neumann didn't know about, like cache hierarchies, latencies, and things like that. So if you consider that part of the von Neumann world, which I do, then the answer is yes. But if you consider concurrency and the machine architecture complexities beyond the von Neumann model, the answer is no. As usual, the answer is it depends on your definitions.
You mentioned teaching in the earlier part of your presentation. So I think many people think that C++ may have like a steep learning curve. So what do you think is the balance between functionality and being easy to learn?
I think people are teaching C++ all wrong. And I have been saying this for at least 20 years, probably 30. And one of the problems was we couldn't teach teachers fast enough on the growth curve. So there's people who think that it should be like C and you teach C first. You have to learn to make all the mistakes first, and then you can try and fix them later. You have to have macros, void stars, range, buffer overflow. It's apparently good for you. And then, of course, you never get the second course to fix it. Then happened to be very influential at the time was the Java stuff. All object-oriented, all pure, not the pollution that you get from C++. Because there you can do other things. Hey, you can do X plus Y without doing a dynamic call and without having a class hierarchy. No, you mustn't do that. That's bad. So today you get a lot of code where there's classes upon classes and hierarchies and hierarchies just because it's supposed to be right. In my opinion, most classes are standalone. They're not part of a hierarchy. Which hierarchy do you want your point or your pixel to be part of? Then at the next level, you have what needs a hierarchy, like the control of an electric engine on a plane. There's different models of electric engines there. There's the standard hierarchy, you get the virtual function, you get into the right kind of motor controls. And then in the end, you have some cases where you want multiple inheritance because things are modeling different things in the real world. I got a question as late as last month about how great multiple inheritance is. No, it's not great. It's part of the original view of what representing the real world is, and you need it 1%, 0.5% of time, because it's 3 levels down. Now, for teaching C++, I was put to proving it. Somebody showed me at Texas A&M, where I was at the time, they showed me their programming course. And I expressed myself rather vocally about it. And they said, "You think you can do better?" Of course I can do better. So I was in charge of it. And I looked at the textbooks and I came out with smoke coming out of my ears. I mean, if that is C++, I don't like it either. So I had to write a textbook. I had to conduct a course. It's not universally used, but it is used very widely. If you want to know my opinion about how to teach novices, look at the book with Swanson. And I can assure you, I have taught many thousands of beginning students that knew of no code at all when they started, and they could do fairly decent graphical and computational stuff after 3 months. If you are already a programmer and you know the basics, everybody here is beyond that level, right? You look at a book called A Tour of C++, which is just an overview of what C++ is today. Because a lot of people have this view that C++ sort of is stuck somewhere in the 80s. And I showed you the graph. There was a reason to show you the graph. Things improve. That's engineering. Actually, yeah. We're gonna have that. Oh. Oh,
Sorry to disappoint. I had to cut that short. We are on a schedule here since we have the other 2 regions that cannot push back their time. Thank you so much. That was very informative. I know we've had tons of more questions for you. But at this point, next up, we have straight from Texas. This is ICPC Executive Director and ICPC Foundation President, Dr. Bill Poucher.
Well, thank you. I sort of become a trademark for me to wear my Stetson, and you know, they do last a long time. One of the things they do is they keep me from going blind when there are lights like that. That's actually why I started using it at ceremonies. And of course, in those days, a lot of flashes that really were hard to deal with. But there is something about this hat that I think is symbolic of Texas. It's first of all, it's gray belly. It's not white. You know why? Well, because no matter how hard you tried to wear a white hat rather than a black hat, the world, you know, makes you have to find something that you can live with and that others can as well. So this is called gray belly. And over the last 100 years in many places in Texas, when it was time to get together, so that people had the opportunity to voice their opinions, and people had the opportunity to listen to them. Then somebody would agree to wear the hat, and their job was that everyone had the opportunity to speak and to listen. That's a very primitive concept of all universities. And it's a great pleasure to be here at Columbia that preserves that tradition and offers you all this wonderful opportunity to come together and for the rest of your life to be an ICPC alumni who represented your university, either as a result of competing in the competition or volunteering to make it happen. And so I'd like to simply say thank you to all the people who made that happen. And right now I'd like to have the coaches stand up. If you're a coach, I'd like to recognize. I'd like to simply say that there, in all great and human endeavors, there are multiple reasons to do this. The number one is that it speaks to your heart, because you see your students excited about living, excited about building, excited about giving, okay, and the performance, their performance going way up, and their peers' performance going way up, because if the performance goes up in part of the classroom, it increases in the entire classroom. And since the classrooms keep getting bigger and bigger and bigger, it's so much easier to grade exams when they get all the answers right. You know, so anyway, thank you very, very much. And to the volunteers, please stand. Well, they're probably all working somewhere else, but Joe and John and Christian, you've really assembled a great team. And I can tell you, John had competed in 86 and has 40 years of experience serving the ICPC community, and that is who we are. We're part of the infrastructure of civilization that builds communities, and that's what your university is. Oh, someone will say it's a creature of the state of so-and-so because they have to fill out a form. Okay, fine. But the reality is that you're the form we want to see fill out, okay? We want to see you have opportunity, and it's a privilege to be here. So I do want to share something with you. Now, I came from a tradition in which everything was memorized to be delivered on board because, well, we didn't have PowerPoint back then. On the other hand, I think I'd like to just share something about somebody I think was really, really special. And we're actually all students of this person. And what this person wrote, was that excellence is an art won by training and habituation. We do not act rightly because we have virtue or excellence, but we rather have those because we have acted rightly. We are what we repeatedly do. Excellence, then, is not an act, but a habit. And the ICPC, I hope, is habit forming for you in your life as the problem domain changes, as the team changes, okay, and as you create opportunity for the world to come. So you see, it's really cool that life gives life if we give life. And the ICPC is part of that life. And we're really simple. We exist to lift you up and shine the spotlight on you, and to encourage you to create systems that benefit your neighbors together. It's not that we don't care about all the other things that are happening around us. We're trying to make a difference and for it to be habit forming for ourselves and our neighbors. Well, that's it. Thank you.
Thanks, Bill. I think at this point, Greater New York will separate from the other two regionals. I wish everybody best of luck in Northeast and East Central. Ivana, Bob, if you have any parting words.
Yeah, I'd like to thank Bjorn for his talk and Bill for his words of inspiration this morning. Good luck to Greater New York. Do well. Have fun.
The same from us. All the best to all.
Okay, thanks. Good luck, everybody.
Okay. Hi, everybody. Welcome now to only two regions simultaneously. I am Zach Butler. I'm the Deputy OCD for Northeast North America, and I know we are on a tight time schedule, but there are some important bits that I want to make sure we all know before the contest gets going. So, as you see, we are now two regions.
Greetings, Greater New York, East Central, and Northeast regions. I'm Tony Logar, Director of ICPC North America. Thank you for inviting me to your competition. I wish I could be there to see all of you in person, to see your excitement, to feel the energy and the nervousness, to watch you all perform at the high level we've all come to expect from the teams in your regionals. I applaud the experiment that you're conducting this year, having all three contests on Sunday, and increasing inter-regional cooperation. The hope is that the RCDs will be able to do more as they coordinate some of the tasks common to all three regions. I can't wait to watch this year's contests, but no matter the outcome, I congratulate all the contestants. You are the best of the best, and you should be enormously proud of the hard work and dedication that has led you here. Most of you had to survive hard-fought local contests to earn the right to compete in this regional, and all of you have spent countless hours preparing for this moment. This competition brings together the best problem solvers from across North America, people like you, the problem solvers who will build a better future for all of us. I'd like to comment on what it means to compete. We focus an awful lot on who advances to the North America Championship, but there are lots of ways to win this contest. You might beat a rival school you have never beaten before, or be the highest finishing team in your state, or have the highest finish in your university's history, or solve the greatest number of problems your team has ever solved, or have your best day ever as a competitor. In every one of these situations, you won this contest. And at the end of the day, you will all be winners because you competed at such a high level, and many of you will also be winners because you achieved the goal you set for yourself. And so on behalf of the hundreds, possibly thousands, of North America volunteers who work to make these contests a reality, I congratulate you on being here today, and I extend a warm welcome to the 2023 regional competitions. Speaking of those volunteers, contestants, if you haven't already, please be sure to thank your coaches for their guidance, leadership, and dedication to helping you achieve your goals. I coached for over 30 years and loved every minute of it. And to be honest, I still miss it, but I know how much of an effort it requires. Coaches, you are the backbone of our organization. We can't thank you enough. North America volunteers are working to help you by providing training materials and curriculum through ICPC University, with mentorship programs to pair seasoned coaches with new coaches, and by evaluating and upgrading our coach recognition efforts to help you professionally. Thank you for all you do. You know, ICPC is so much more than just a programming contest. We are a community dedicated to providing opportunities to folks who want to be great problem solvers, and we have fun doing it. So when your time as a competitor is finished, I hope you will join the ICPC family of volunteers and serve as a problem creator, a judge, a site director, or a coach. We'd love to have you. You too can work with amazing people like Joe Terlizzi, John Buck, and Christian Lim, the dream team of Greater New York, or Bob Kramer and Ed Shanofsky and their team in East Central. The only difficulty there is learning to spell Ed's last name to send him an email. Sorry, Ed. Or the superbly competent and always entertaining duo of Ivana Bezakova and Zach Butler in Northeast. I hope you all realize just how fortunate you are to have such superb leadership teams in your regions. These folks are innovative, inspiring, irreplaceable, impactful, impressive, and a whole lot of other words that start with I. And you and I and all of ICPC are lucky to have the opportunity to know and work with them. Thank you for inviting me to say a few words at your competition. But now I think it's time for me to stop talking and for the contest to get started. I wish you all good luck and a good time. And when the energy starts to lag in hour 4, remember the rallying cry from that immortal film classic, Galaxy Quest. Never give up, never surrender. Have a great regional.
contest is going to be starting in a little bit. Can you guys hear me? Yeah, so the contest is going to start in about 2 minutes. Until then, we're just waiting. I think the North. So this contest, there are 3 contests happening at the same time. There's Greater New York. Oh, sorry. Let me turn this music on. There's Greater New York. There's NENA, Northeast North America, and East Central North America, and they might have started already. So let me just drop some links to those. So those contests, that contest has a mirror on Caddis that probably you can see. And that contest has actually already started. That contest only shares a few problems with this, so it shares like 8 problems, so it's probably not going to be identical. But it is, it should be similar. Let's see. I don't think there's going to be a mirror for this contest. So for this contest, it's just going to be, we'll just talk about the problems as they come up and see how it goes. All right, and it looks like it might have started. And so let's go hide this clock. And I can turn off this as well. Hey. Okay, so. Yeah, we have everything showing. No submissions yet. We'll see when the first submissions start coming in. I think the contest has started now, but don't have access to the, don't have any confirmation yet. Yeah. See how it goes. How are all of y'all's day going? While we're waiting, we might as well start taking a look at some of the problems in NENA and ECNA. Easiest place to find those is, I think there's a mirror. There's a mirror here. Let's see. And so, yeah, we can just start looking at some of these problems. Let me pull up the standings. I think in the opening ceremony they told us that A was going to be the easy problem. So we'll see if teams solve that quickly. Right now I don't see any submissions still, which I hope means that they're still solving and not that the contest is broken. But we'll see. Yeah, we're still pretty early in the contest. It's just 3 minutes in. Okay, so we see our first submissions coming in for A. I think A is one of the shared problems. I'll grab a problem set from the judges as soon as the contest starts proper. But Cornell is the first team with a correct submit. 3 minutes into the contest, 3 minutes of penalty. 3 wrong submissions already. It's kind of surprising. I think A is supposed to be the easy problem, and I think A also matches the easy problem on Nina, but it might not. So we can just look at the Nina easy problem. Let me. Thank you. Cool. Okay, this does not match the Nina problem A. Problem B is. Okay, cool. I have a physical copy of the problem set here. So we can, yeah. Great. Sorry, I'm still muted. All right, here's the problem set. I pinned the message in YouTube, so that should be good. So now we can start reading the problems in earnest. So it looks like problem A actually doesn't match the Nina problem A. Problem A is, I guess, supposed to be easier. and problem B is problem A from Nina. So yeah, why don't we just start reading these problems and talking about them? We can go pretty slowly. Problem A, corn farmers need to do pre-harvest yield estimates to determine the appropriate number of bushels of corn that the farm will produce. Let me take some time and let me take a sec and try and share my screen. Let's see. Okay, you know what? Let me do this. So I'm in a classroom to cast, and unfortunately, this classroom seems to only have this classroom has a monitor in it, but it seems to only have a VGA cable to connect to the projector or the monitor, and so I'm trying to find a way to connect. And hopefully, that way I will be able to stream while sharing my screen. Let's see if I can get something working. Yeah, let's just unpause this. No one will care. Okay. Cool. Great. I can put this up here. Okay. Yeah. So now. Okay, cool. So let's put this behind. How do you transform these trees? Okay, cool. Let's just cover up some of this. Okay. Yeah, we don't need all this on the side. So let's. Okay. Yeah, we'll just put this on top of the scoreboard. And then some stuff. Transform. Okay, yeah, this is probably a little small right now. Okay, yeah, whatever. Here's problem A, so that we can look at it together. And so we are, yeah, some questions from chat. Why don't I stream anymore? You know, was just busy and time and stuff. But here we have, okay, let me just. Okay. Sure. Push this up here. Okay, cool. Okay, great. Yeah, okay. So we can, yeah, let's just spend some time and read some of those problems and try and solve some of the easy ones together. Corn farmers need to do pre-harvest yields to approximate the number of bushels of corn they'll produce. They have to, you pretty much estimate it based on the ears of corn that have formed and the kernels. And so, standard way to estimate corn yield is to calculate number of bushels of corn per acre. In a section of 5 ears are chosen at random. For each ear, the number of kernels is counted and multiplied by the number of rows of kernels, kernel weight factor. So, total number of ears, total number of kernels, and then divide by the kernel weight factor. Quotient is the number of bushels that they expect to harvest. All calculations are done as integers with no rounding. Interesting. Okay, so what we should do is pretty much just do what the problem says, right? We should find the average number of kernels per ear, which is it seems to be a yeah, average number of kernels per ear is say 512, and there's 25 ears, then the KWF is 85, then you get 150 bushels. And okay, so the input consists of 2 lines. You're given the ears of corn in terms of the kernels around times the kernels long, which is as you multiply these two together and then add them up, and then you take and then you multiply by the number of ears in the row and divide by the KWF, and you do it in integers. I'm not exactly sure what integers means here. Maybe you floor it, maybe you ceiling it, but maybe that's why some of these teams have it wrong right now. I guess most teams at this point have kind of solved this problem, but some teams haven't. By the way, I wonder why I'm not seeing the problem queue in my overlay. Let me check on that. Maybe I just don't have access to the queue. Okay, it seems like the queue is a known problem. But yeah, let's see. While teams are still solving these easy problems, let's just go start typing up some of them. So I'll just start typing some of them, and yeah, we can kind of just solve them together. Let me find a better place to put this screen. Let's see, transform. Because there's no queue right now, I might as well just use this space. So I'm just gonna go put this here. Okay, cool. We can just put our problems here. All right, so yeah, let's just solve some problems together while we're reading. So let's see. Let's just make a folder. Cool. Let me show this. So I don't have a place to submit, but I think the problems that are shared we can submit to Caddis, and the problems that aren't we can do something else. Do I plan on uploading more screencasts? We'll see. We'll see. It kind of depends on, just my free time and stuff. But if possible, I'll probably try and do some more. All right, so A. Okay, so A, what we're going to do is we're going to read in 10 pairs of integers. 0 is less than 5. Yeah, we should use loops for this because, it's, it'll be a little bit easier to read our code. Here, let me shrink this a little bit further. Put this here. Okay. Sorry, that it just like makes it so that we don't have to like do the same thing 5 times. So we're gonna have a area around and long, and these two together give us the number of kernels, right? So int total kernels 0 total kernels plus equals a times l. Total kernels average kernels equals total kernels over 5, and then we get the number of ears of corn. We get the number of ears of corn in a row. So this equals average kernels times n kwf. Read them in, divided by kwf. And we're supposed to do these all in integers, but I'm not exactly sure what that means. It might mean that it's always a multiple, but that doesn't sound right. So yeah, I'm not quite sure what that means. It might just mean that you round. Sample 1.out, 150. Oop. Sample 2.in. Example 3.out 150. So we can test this real quick. Okay, seems fine. So I don't have a place to submit it, but you know, we'll just assume that it's correct. Let me open up some other scoreboards here. Let's see. Great. Okay. Okay, great. Here's chat. Now, okay, cool. Yeah, so let me okay. Cool. Okay, sure. So let me bring up, these are the standings for NINA, for Northeast North America and ECNA, which share a bunch of problems. They don't share problem A. Problem A is not one of the shared problems, but you know, you can look at this. Let me just go pin a bunch of links. So the GMY problem set is here. You can't do multi-line. Is here. Mirror is here. Place pin message. Okay. Great. Okay, so these are all the things. Yeah, okay. Let's just keep going through the GMY problems then. Oh, they have all the zip files too. I guess I might as well download them then. Okay, so what was the format? Problems. Okay, cool. Okay, anyways, well, that's just a little more convenient. Okay, but cool, let's go look at problem B. So problem B here, which 15 teams have solved, it seems pretty clearly to be the second easiest problem, is shared with NINA and ECNA, and it's this problem. Might as well open it here. So it's problem B here. It's called a pivotal question. Let me zoom in a tad. Okay, quicksort is a recursive partitioning algorithm. Let's see, can you guys read this? It looks like barely big enough. You can follow along on your own. Okay, quicksort is a recursive sorting algorithm developed in 1959 by Tony Hoare. Major steps is a partition step. How a partition is executed and a pivot element is selected are fascinating questions, but not of interest. What we're trying to answer is, given an array, determine all values that could be the pivot value, assuming it's been partitioned, or determine that the array has not been partitioned. And one thing to note, when you're partitioning an array, you have to worry a little bit about ties, and it says that rearrange the elements so that all elements on the left half are less than or equal to, and all elements on the right half are strictly greater. And so we are just trying to find all elements which are, did my internet just drop? Let's see, this internet connection looks not very good. Okay, looks back up and fine. Okay, I dropped 200 frames, which is not a big deal. Okay, cool. Yeah, okay, so that's pretty straightforward. One thing we can do is we can take prefix maxes to check the prefix and suffix mins to check the suffix. So yeah, let's just do that. Let's make this problem. I'm using, so here I'm using like a bunch of pre-set up things. But one thing about this is an ICPC contest. So all the contestants should be using clean images with nothing on them. What they can do instead is they can bring 25 pages of pre-written reference document. It's called a team reference document. And they can bring that in order and use that as their reference. So they can copy paste from it, and they can, they can't copy paste from it, but they can type anything that's written on it into the computer. And so that's the only pre-written code or pre-made things that they're allowed to use. Everything else has to be done in contest. But you have 5 hours, so if you just spend the first minute like typing up your normal template and typing up like, just typing up a makefile, it's totally worth it. So like that's what I would usually do. That's what we usually did in contest, and that's probably the best. That's like it's never too slow. Okay, so output the number of values that could have served as the pivot to partition the array. If m is greater than 100, output just the first 100 of these. A value of m equals 0 indicates the array is not partitioned. Okay, so int n vector int an. Also, you can see I have Copilot turned on here, but Copilot is obviously not allowed in the actual contest. That's an interesting question. I don't know, does anyone want to weigh in on whether they think Copilot and other AI tools should be allowed? So we can do this with 2 passes, but we could also do this with 1 pass. What we could do is, one thing you can observe is that all pivot elements have to be strictly increasing, right? There's just, there's, any element is the pivot until you get to something that's smaller than it, and then neither of these two can be the pivot. So we could just keep a stack of the elements which could be the pivot. So let's do that. Pivots.reserve n. And so what we have to do is we have to keep the kermax, and we also have to keep these pivots, and then I equals 0, I is less than n. So while pivots back not pivots dot empty and pivots dot back dot first, we're going to keep the value and their index is less than or equal to AI. Then pivots dot pop back. So pivots just are not allowed to contain elements that are smaller than our current element, right? And then also if AI is greater than curve max equals AI, and also we can push it into the pivot. So pivots.inplace. I don't like inplace back. Push back AII. Okay, and so this just gives us all our pivots. And now we can print it out. Pivots.size, and then I equals 0 is in pivots.size, but I is also less than 100. And then we print space and then pivots I.second. Print a new line. Okay, so that's all here. It's kind of interesting that the sample input is a single line. I feel like people usually and so looking at the sample, I actually got this wrong, right? We're supposed to be printing out the values and not the indices, which is pretty easy to fix. We can just we just don't have to keep the indices at all. Okay. And then pivots I.second, or pivots I. Okay, so we print the first 100. If there are multiple, we print the first 100 and all of them if otherwise. So we have this sample wrong. I wonder what happened here. So pivots.back, curmax equals A0, if AI equals curmax. What is wrong here? Pivots.popback. Here, we'll use enhanced for. I wonder what is wrong. Pivots.empty and pivots.back is less than or equal to A. Oh, sorry, this should be greater than or equal to AI. Yeah. Because if an early element is greater than or equal to U, then U cannot be a pivot. Okay, yeah. Okay, so we can actually submit this. We'll just join this contest. Our scoreboard is kind of going to be a little bit wrecked, but that's fine. I don't need a team. Okay. And then let's go back. Contestant. Okay, so we can just submit to a pivotal question. We should check really quick to see if the Nina one is the same. But it probably is. Okay. So I didn't join the contest? Okay, great. And then submit. Okay, sure. So let's just submit this and see how it does, see if it gets it correct. Okay, so this passes. Easy enough. Okay, and we can take another look at our scoreboard right now. It looks like the problems that have solves are A, B, D has 5 solves, C and I each have a few. And so it's like a pretty, it's pretty normal. It's been half an hour, and the top team has 30 problems. And so, yeah, that's like pretty normal. Here, let me show this again. The top team has 3 problems, and yeah, that's not too far off from what we'd expect. You know, people are solving different problems and reading different problems. So I think if we're going in order of difficulty, we should probably go look at D next. Oh wow, and Cornell Kappa just got their first solve on K. Okay. So yeah, it looks like a lot of these problems are solvable. We'll have to keep waiting to figure out which problems are the really hard ones. But for now, we are solving. We'll just track through the ones that we know are easy. So let's look at problem D. D. Double up. So a double up game consists of a sequence of n numbers where each AI is a power of 2. In one move, you can either remove one number or merge 2 adjacent numbers into a single number of twice the value. So this is like Suika game or like 2048, right? Have you guys played Suika game? It's this thing that's been going around on Twitch and stuff. I think it just came out it's been on the Japanese Nintendo store for like a bit, and I think it just came out on the international ones. English version just came out, but pretty much it's like 2048 but with physics. It's supposed to be interesting. Anyways, enough. You hate Suika game. I think the Switch one is probably better, right? We should probably I think maybe we should try and get the Switch one and try playing that. Anyways, okay, so you can. So what can you do? You can either remove a number or merge 2 identical adjacent numbers into a number of twice the value. And you play until a single number remains. So what's the largest number we can obtain? So the point of this game is pretty much well, we might as well do all the removes first, right? There's no real reason to keep numbers in. And then you also kind of might as well merge numbers while you can. So that's probably the main idea. Yeah, all we need to do is, we just need to parse them and store them this way. What's the largest number we can obtain? One interesting thing is they gave us really large numbers. The numbers are up to 2 to the 100. Those are kind of annoying to deal with. I'm honestly really surprised that they give numbers this large. I guess maybe the problem is too easy to cheese if you don't have bounds this big. The max possible value you can get, the sum is constant, right? So the max possible value you can get is about 2 to the 110, which fits in int 128. But int 128s are kind of annoying to work with. So maybe you're just supposed to take log and then print it out and then do it with big nums. But that sounds pretty annoying. But why not? Let's just do it. So yeah, let's also check real quick if it's this is problem E. The easy problem E was also in Nina. It was just in a different order. So let's go submit problem A. Might as well submit it. I didn't realize it was in here. Yeah, we'll have to, I guess, so we haven't gotten to any problems that aren't shared yet. So all problems here are shared. One interesting thing is a lot of contests like to put the, to discourage you from getting the book prize. Yeah, so actually, if any of you guys watched the opening ceremony, Bjorn Strusup, the creator of C++, gave a talk, and apparently there are 5 signed copies. There's 3 signed copies of his book that are a prize for the team that solves the most problems using C++. And so for those of you who haven't been on the scene very much, pretty much everyone here uses C++ for pretty much every single problem. So it's probably just going to go to whichever team solves the most problems, probably the fastest. It'll probably just go to the winning team. But there are some times when you might want to use some other language. Like for this problem, double up, Python has, big integers are much easier to use in Python than in C++. And so maybe people will actually try and solve these problems in Python in order to get the book prize, and lose the opportunity to get the book prize. But yeah, let's go implement problem D. Yeah, by the way, looking at Nina standings, we can also see that ECNA Nina standings, A is definitely the easiest problem. A and E, which are A and B in this problem set, are the easiest, and then F has the next most solves, and F I think is D in our problem set. So it seems like the two contests are shaping up pretty similarly. We have some people still solving other problems. A handful of problems each have one solve, C, I, and K. But beyond that, it's just these 3 problems. So let's go finish implementing D and wrap up this really easy part of the contest. Okay, so so the main idea here is just going to be, if you have 2 numbers that are the same, you might as well merge them because, well, what we're going to do is we're going to go left to right, and then we're always just going to have a decreasing sequence of numbers. And if you get a new number and it's bigger than someone's, then kind of your sandwich isn't really able to do anything, you know, because it's bigger than this small. Like if you have, here, let's go look at Suika game. I bet there's some here. We'll use online version of Suika game as a demonstration tool. Okay, so you gotta go build some stuff first. So the point is that if you have this guy in between these 2 guys, which are both big, this guy, the middle one is kind of useless, right? And so we really should just always remove him. And similarly, if you have these guys between these things and everything else is going to fall to the right of them, then these guys are just kind of in your way. And so you really should just remove them, and there's no point in keeping them. And so I think that's what we're just going to do. So let's auto read log. Okay, so what we're going to do, int 128t v equals 0. V times 10 plus c minus 0. Yeah. So we're going to just convert this to an int 128, and then int a equals 0, while v not vm1, v1, a plus plus. So we're just going to take the log, surf v equals 1. So we're just going to take the log of all these numbers. They all start off being powers of 2, right? Or maybe they don't. Where each AI is a power of 2. Okay. Yeah. So now we have our A, which is our value. And now while stack empty stack back. So while there's things in the stack that are smaller than A, these things are pretty much unusable. And then while not stack.empty and stack.back equals A, if we have something that equals A, then we can actually merge with it. And we might as well merge with it because you kind of should greedily do your, oh, sorry, let me go back to coding stream. You kind of should greedily do things from left to right. That way you'll have, as long as if you merge the first 2 that you get and the next 2 that you get and the next 2 that you get, you're kind of guaranteed to not have any silly even odd parity issues. So because we're doing it from left to right, it's actually fine to just do this. So stack.popback, A++, and then stack.pushback A. Okay, cool. So our stack is always decreasing, and then it's our value. So the best value that we can get is the first element of our stack. So assert not stack.empty. If n is greater than 0, our stack is never empty at the end. Ants equals stack of 0. 128t 1 left shift ants. And now we have to convert it back to a string. So string s while ants 10 s plus equals car 0 plus ants mod 10. Verse esta. Okay, so then we reverse it and print it out at the end. There's another way you could do this, which is you kind of consider all the smallest guys first, and then because they're all smallest, right, everything between them is like bigger and will block them. So you kind of have to merge them. So if there's a bunch in a row, if there's an even number, you merge them all. If there's an odd number, you merge them all and then delete the last one. And then you like collapse those guys together, and then you go to the next level. This is doing functionally the same thing, but just in a different order. Okay, so let's go try submitting this. We're going to go submit this to problem F. Oh, we got this wrong. I wonder why. This is stack of 0. Okay, so let's try submitting this to F. Yeah, pasting is easier. What? Did I not? Okay, I accidentally deleted this line. Okay, and let's try submitting. Okay, and it passed. Great. So now we have gotten through all the easiest problems, all 3 of the easiest problems. I guess the next problem, yeah, sorry, I can show you the code again. The next problem to look at, let's go back to the problems. The next problem to look at seems to be problem I. Let me see if I have a static scoreboard. Oh, okay, I have the, whatever, it's too late. I've decided to cover up the queue already. Okay. Whatever. We can, here, let me move this stuff upwards a little bit. Okay, great. So that we can see the queue. Okay, so yeah, we can see the queue of problems coming in underneath. I don't see any like super standout, anything that's like super standing out yet, but we can keep an eye on the queue. Okay, great. Yeah, and so it looks like, yeah, nothing super crazy. I wish I could see a scoreboard with the top teams. I wonder if that is possible. Let's see. I think it'll be in the ticker. But otherwise, I don't think I have access to one. It would be pretty interesting to look at some team submissions for B. There are a lot of wrong submissions for B, which was the pivot question, and I am kind of curious, you know, what kinds of things people are doing wrong. So maybe later in the stream, I'll like ask the judges to see if I can look at other people's code. But for now, let's just keep going. Let's look at problem I. Problem I is it's down here. So as you guys can tell, like ICPC contests are not sorted in difficulty order. I think this contest told us that A would be the easiest problem, but other than that, yeah. Okay, so I and C are the next 2 problems. So ISBN conversion. An ISBN is a unique identifier, and the last digit is a checksum. So interesting. So the checksum, you compute it using some particular mechanism. it looks like one of them is mod 10 and one of them is mod 11, but that's fine. And so in ISBN 10, because it's mod 11, sometimes the checksum could be X. And I bet we're just supposed to check if they're valid. Maintain the existing positions of any existing hyphens. Okay, so we're trying to convert from ISBN 10 to ISBN 13. And we are supposed to, yeah, we're supposed to just replace may contain up to 3 hyphens, but it cannot begin or end with a hyphen. Okay, so the last thing is always the digit, and then the first thing is always the thing. So we're really just supposed to compute, we're supposed to check the ISBN 10, and then compute the, compute an ISBN 13 if it's valid. Okay, so we have to go read the ISBN 10 hyphen rules because we have to check those too. So it consists of 4 parts, which means they contain up to 3 hyphens. It cannot begin or end, and it cannot contain consecutive hyphens. If there are 3 hyphens, one must separate the checksum digit from the digit that precedes it. If there are fewer than 3 hyphens, it could be anything. Okay, so let's just go implement some rules. Let's see if we have a way to submit this problem. Okay, it is on this contest as well. That's interesting. All right. Okay, so should be easy enough. Okay, so let's just write some templates first. So int n is the number of cases for t string s. And we'll write optional string solve string s. If ants count. Oh, okay. Else. Okay, so, oh, sorry. Let me turn the code back on. You only checked that the position of the pivot was correct, not the greater less than. Oh, yeah, no, that's okay. Okay, so yeah, let's yeah, we can do this, and now we have to check a bunch of things, right? So in num. So first of all, there have to be 10 digits, right? And possibly 1x. Okay, so let's see, how are we going to do this? Okay, so num hyphen num digit equals 0, x equals 0. For car C and S, if num, okay, so x, num digit not equals 9, return null opt. So if the, yeah, if num x x plus, okay, here, just say equals C 0 is less than equal to C, and C is less than equal to 9. Num digit plus plus. Else if C equals hyphen num hyphen plus plus, else assert, else if it contains other digits, then it should be bad. Okay, so if num digit not equals 10, return null opt. Okay, we need exactly 10 digits. If num hyphen 3 is strictly greater than 3, it's also bad. All right, let's go check no starting or ending. So if s is 0 equals hyphen, return null opt, go front and back. Si equals hyphen, si plus 1, hyphen, then we're also bad. Okay, so no 2 consecutive, and then if num hyphen equals 3 and s of s dot size minus 2 not equals hyphen, return. So if there's 3 hyphens, one of them must be in the second to last position, separating the checksum, right? If there are fewer, then it doesn't matter. Okay. Okay, great. So now I think we've constructed this. So now we just need to compute the checksum for the rest. So string res equals 987 dash plus s, right? Res.popback. So now we also have to go check the checksum. Go check the checksum for. Okay, so here we'll just do this. So in sum, sum equals 0. So sum plus equals what is it? Num digit, 10 minus num digit. Right, 10 minus the number of preceding digits times 10. And this is sum plus times c minus 0. We'll just do sum 1 equals 11, just to be safe. So if, and yeah, sum not equals 0, then we're bad. Okay. Okay, so now we need to compute the thing for we need to compute the last digit. So res for I equals 0, I is less than 4. New sum equals 0, car w equals 1. Here, we'll do it this way. We'll be kind of lazy. For car c in s, c equals hyphen, continue, assert 0, c, and c is less than 9. New sum plus equals c times 0 times 9 times w, per w, cur w, xor equals 2. So that flips it to 3. So assert cur w equals 1, new d equals 0, d is less than 9, if new sum plus d mod 10 equals 0, car 0 plus okay, let's do it better. Okay, so res plus equals car 0 plus new sum mod 10 times 9 mod 10, sure, whatever. Okay, so that should work. So let's see if it works on all these samples. So at this point, looking back at the scoreboard, we also see a bunch of submissions for C coming in. It seems like a lot of teams are taking a bid on it though, so that's kind of interesting. So we're computing the checksums wrong. S must be a multiple of 10. So new sum plus equals cur W x equals 2. So everything seems to be fine except our new checksum computation. So what we're doing is we alternate 1s and 2s. Oh, sorry, I screwed this up. This is supposed to be 987, not 978. That's actually what the checksum is supposed to check, kind of. It's good at checking, because it's alternating 1s and 2s, if you swap two adjacent digits, then the checksum will change. So it actually, I actually kind of got saved by the checksum itself, which is pretty cool, Okay, let's go submit this. And hopefully it passes. This seems like the type of problem where you can get a lot of wrong submits, but I'm kind of surprised that a lot of the teams that passed it don't have any extra submissions. But yeah, it seems like we are doing fine. It is taking a bit of time, which is a little surprising, but we're doing some string operations, so maybe that's just how it is. Okay, but it passed in 0.0 seconds. So, okay, that's good enough. Okay, so pretty clearly the next problem to look at is C. C has about as many solves as I, and with this new submit coming in, it might pass it. It might actually have more. And then K. All right, so let's look at C. Problem C, the callet's function on positive integers. Okay, the collet sequence. Returns the smallest integer for which the given sequence is CST. Oh, okay. So pretty much we're given a collet sequence, and one thing about the collet sequence is pretty much if you know the parities, right? Professor Fumblemore needs a program which allows him to enter a sequence of E's and O's and returns the smallest integer for which the sequence is CSTN. Okay. How big are the bounds? It's up to 50 letters. Okay, which is kind of long. Okay, so what we can observe is that pretty much every time we go forward, it is always a linear function of n, right? We either divide by 2 or we multiply by 3 and then add 1. And so pretty much we start from this thing, and then we need to end at a power of 2, and we just have this linear function. The denominator is going to be it's going to be something like a times n plus x divide by 2, divide by some divide. It's going to be, the coefficients are going to be rational numbers, and the denominator could be a power of 2, and so all we have to do is and so we just need the denominator to be a pretty nice power of 2. Let me think about this. Hey-o. So okay, we can probably just write something which looks for this. The answer is always going to look like a power of 3 times n plus some number divided by a power of 2 equals a power of 2. And so we're looking for the smallest power of 2 which matches. Smallest power of 2 above something which matches. And so we could just kind of check powers of 2 or something for that mod 3 value. And so that's probably what we should do. Yeah. inputs will be chosen such that n is less than 2 to the 47. This is also a problem where it's like a little unclear if all numbers are going to stay under, like are going to be small enough. So you really kind of would like to use, would like to use big integers. But in this case, what's 3 to the 50? 3 to the 50 is over 2 to the 64. 3 to the 50 is bigger than 2 to the 64, right? Which means that, like, yeah, if you just keep doing odd operations, then oh, okay, right. There can't be two odd operations in a row. And so it is the case that only E's and O's, N's and O, and no two O's are adjacent. Okay, so that is, we can just check. We can just check that. Okay. Then, yeah, we can just implement this. Let's just go implement something. I think we don't have to worry about integer overflow, and I think we can just naively check numbers. So let's just do that. C. And we can use int128 if we're like concerned. So. Okay, so there's just a single string. Const string invalid equals invalid. Let's just make this here. So if C equals E or C. If C not equals E and C not equals O, count invalid, and then exit 0. Okay. Back, not equals O. And we'll print invalid as well. And then if s dot back, okay, and then for int I equals 0, I equals 1. Si is O and I plus 1 equals O. Plus 1 equals O, then also count invalid. Okay. Okay, so now let's just compute this linear function. So int coef A equals 1, coef plus, I don't know, const, add equals 0, and so we're going to be coef times n plus add divided by denom. So for car C in S, C equals E, then denom times equals 2, else if C equals O, then we multiply by 3, so coef times equals 3, add times equals 3, and then we add 1, so add plus equals denom. Okay, and so the goal is whatever we put in should become a power of 2, so let's just casework on which power of 2 we end up with, right? So for int, and I don't really know how big these things are, so we'll use int128t. Using i128 equals int128t. Okay, so for int a equals 0, int target equals 1, target true, target times equals 2. Okay, so what we need to do is let's check what n is. So n equals denom times target minus add n if n mod coef not equals 0, continue. Break. So if this is too big, then we'll just break. And otherwise, if n mod the coefficient is not 0, we're told that the n will always be at most 2 to the 47. So if n is greater than or strictly greater than 47, then we're just out. If n is at least, coef times 2 to the 47, then we're out. N mod coef not equal 0, and okay, so now we check this. So I128 cur equals n, full good equals false, equals true, s, if c equals o, if cur and 1, if not cur and 1, good equals false, break. Cur equals 3 times cur plus 1. E, if cur and 1 good equals false, break. 2 times cur over 2. Okay. If not good, continue. Cert cur equals target. Count n while n divided equals 10, ans plus equals car 0 plus n mod 10 reverse ans dot begin ans dot end. Okay, and we should also go make sure that if n less than 0 continue. Okay. So now let's try this. Oh, sorry, I forgot I haven't been showing my code this whole time. Q.in. Oops, sorry. I haven't been showing my code this whole time, but whatever. It's pretty much what you'd expect. I like go compute the function and then I print it out. Okay, so compute the function and then print out what I expect. Print out the smallest one. And then I guess here we should just invalid set 0, just in case. So callets, no callets? What is this called? This one is called Professor Fumblemore and the Callets Conjecture. Oh, here it is. Okay. Okay, let's try submitting this. Hopefully I don't get any, hopefully it's not wrong, but could be a little bit off. It's like, there's like a lot of code, so it could be, something could be off. No, but it looks like it's fine. Okay. And so this runs quite quickly because we're only checking like powers of 2 for the final thing. And we got it wrong. Okay, that's annoying. I wonder why. Yeah, I wonder if like the intermediates can get too big or something. That's like possible. So perhaps I should actually translate this to Python. we can do some back of the envelope estimating. So there's only at most 25 O's, right? It's at most 50 letters, so it's at most 25 O's. So if 2 to the 47 times 3 to the 50, so 3 to the 25 is 10 to the 26, and 2 to the 128 is much bigger than that. Or 2 to the 127 or something is 1e38. So we shouldn't really integer overflow. Single decimal integer and positive integers. So if n is less than or equal to 0, let's see. Okay, so string invalid is invalid. Print int s. If c equals e not equal e and c not equal o, or c not equal. Oh, this is not and. This should be or. Oops. Okay, so I did not successfully check. But I thought I should have failed this assertion, so that's kind of strange. Or sorry, what? This should be and. If C is not E and it's not O, then we output invalid. If the back, if it ends in O, it has to end in O, right? And so, oh, I also should probably check that none of these are, that we don't hit any power of 2 too early. I don't really think that should happen. Oh, I guess it could happen. Okay, so occur if occurring occur minus 1, 0, good equals false. Break. So we're not allowed to contain any powers of 2 in the sequence unless, so this checks if it's a power of 2. So if CST is an empty sequence, I think that means, yeah, E's are even numbers which are not powers of 2. Okay, so we need to check that we don't hit powers of 2. That's an interesting gotcha. Okay. So let's go resubmit this. Hopefully this passes now. Okay, so now this passes. Huh? No. Okay, yeah, now this passes. Okay, here. This is the submission. Okay, cool. So now we've passed, I think that's the same as A, B, C, D, I. And the only two other problems which have solves are K and F. So let's just go read K. K has 2 solves, and then F has 1 solve. 5 problems down. Plus minus 4 squares. Different squared values. Reordering does not give a difference. A plus minus 4 square is a representation as a sequence of 4 perfect squares in non-increasing order with plus minus signs whose computation is the result. First square must be no more than n in non-increasing order. So a square of 0 must be preceded by a plus sign. If we allow minus signs, okay. Okay, so this is just like a DP. We don't have to do this particularly efficiently, so we're just gonna iterate over squares and just count appearances. The same square appears multiple times. All appearances must be preceded by a plus sign, or all must be preceded by a minus sign. Okay. Increasing order, non-increasing order, plus or minus signs whose computation. Okay. So pretty much you can add, the first square has to be no more than n, right? It has to be positive. Sequence of 4 perfect squares and with plus or minus signs. So the first square has to be positive, right? It seems like. And then the remaining ones can be negative. Okay. So let's just go implement. And so because the first one is at most n, then all prefix sums are at most 4n, and at least like, I don't know, like -3n or something. And so we don't have to worry about too large a range. So what we're going to do is we're going to dp okay, so int n. So we're gonna, let's iterate over squares in decreasing order because I think that's the easiest. So for int, the biggest square has to be no more than n, right? To avoid having infinitely many representations. And then we can append a bunch of zeros at the end. So we're not actually gonna worry about it. So int rt equals 1, well, t times rt is less than n, rt plus plus. For rt is greater than 0. Okay, so we're going to iterate over all squares that are less than n in decreasing order. And then tensor int ways of, I don't know, we'll do 8 times n. So the first parameter is going to be, this is going to be pretty standard GP. The first parameter is the number of ways of, the first parameter is how many terms we've used so far, and the second parameter is the current value. So for int I equals 0, I equals 4. 3, j, u equals 1, use. So u is the current uses. Then we're going to do ways of I plus u, v minus u times v, or for int a equals 0, a is less than or equal to u times n. Ways of 0, 4 times n equals 1. Okay, so if a is less than or equal to, and let's make this plus 1 so we don't have to, okay, a equals 0, okay, rt is greater than or equal to 0, okay. So ways I plus u, if ways I plus I a 0 continue if I greater than 0, and so we can't use a negative number in the first one, and also we can't use -0. Equals ways IA. And then we can always use positive, so plus. Okay. Now at the end, ways of 1, 5 times n. Okay, so now, yeah, let's just try running this. So it's a pretty straightforward DP. A lot of teams should be able to get this. Teams should be pretty familiar with knapsack. Let's see if this is in this one. What's it called? It's called plus minus 4 sums. So I guess this is not in Nina. So we won't be able to submit it, but that's okay. We can come back to it later. Or we can just, hope that our code is correct. The code should be plenty fast enough, and I'm not really concerned about anything. So this is just kind of a very standard knapsack DP where you're you know, just storing like the current value and the number of things you used. Okay, let's move on to the next problem, which would be, well, that's A, B, C, D, I, K. And so now we should probably do problem F, and then we can go continue reading the rest of the problems. Looking back at the scoreboard, let's wait till it scrolls to the top. We have a bunch of teams we have a good amount of contention for the lead. Rutgers is in the lead right now with 6 problems. That includes F, that means that they can probably go clean up K without too much problem. And then Princeton, Cornell, and Princeton are next with 5, and then there's 4 problems each. So this is still, you know, pretty interesting. We'll see how things shape up. We do see a lot of wrong submissions on I, which makes sense. I obviously has like a lot of these edge cases that we were looking at. A lot of different things to check. And so, yeah, that's the ISBN problem. Okay, let's look at problem F. Problem F is a forest for the trees. Actually, I'm going to run to the bathroom real quick. So be back in a sec. Let's unmute. Okay, cool. Let's look at problem F. Okay, problem F. We have a robot into the forest. It's gotten lost. We can detect all the trees. The trees are x, y coordinates. All trees are integer coordinates. Tells you the distance, tree relative unknown direction. So the sensor reading is given as a tuple of distance to the right, distance to the forward, and each of the value can be negative since the robot can sense in all directions. Can you find out where the robot will always place itself as an integer coordinate and align to the positive x or negative x or y axis and will never be the same location. Okay, so we're given a bunch of trees, which are the ground truth, and then we're also given we're given a bunch of trees, which are the ground truth, and then we're also given the robot's current sensor readings, which are the directions of the trees relative to the robot right now, and we're trying to place them, and we're trying to just check if they're equal. This is a kind of interesting problem. You actually can solve this. This is definitely solvable without like these positive or negative x-axis restrictions, but they definitely are pretty. These are definitely like pretty make it easier. Oh, actually, maybe the robot cannot see all trees. Each sensor reading is given as a tuple of. First integer is the ith sensor reading given the distance to the tree along the axis perpendicular. Okay, I see. So the robot, what is R max of any sensor reading? The next two lines contain two integers representing the x and y locations of all trees relative to the global coordinate system. Okay, so actually we're only given like a little square of where the robot is, and so we have to kind of detect if they find everything. So this is pretty interesting. And one interesting question is like, what happens if there are multiple orientations at the same location? But I think then you're supposed to print ambiguous. Okay, so because we see at least one tree, and we know there's at least one tree in the world, the easiest thing to do is just pick the first tree and just pick which tree in the real world it corresponds to. And then we can go like check that all trees and all sensor trees are the same. So let's, and before we do that, we should kind of rotate all the sensor readings. We should rotate all the sensor readings because we're not sure which way the robot is oriented. So let's just implement this. So by the way, we can also look at if any teams in NINA have solved this problem. I believe this is problem G on their contest. And so we have only 2 teams have solved this problem on NINA, which is interesting. B has also been solved on NINA ECNA, and B roadband might not be a problem on this problem set, so maybe that's an easier problem that we could look at from their regional. But let's just focus on G and Y for now. So, oh god, E looks like geometry, 3D potentially. Okay, so let's go open problem F. All right, 3 integers, and T and S are okay. So vectors array into trees and T. Y in trees. Interesting. Copilot thought that they're shrubs. Sensor readings. For auto imp. Okay, let's read in the readings. And now, okay, now, so the first thing we're going to do is we're going to do 4 rotations. So 4 int z equals 0, z is less than 4, z plus plus. And we can just rotate in place because that's probably the easiest. So in order to rotate by 90 degrees, you swap the 2 axes and flip one of them. So this is rotating by 90 degrees. And we're just going to rotate all the readings by 90 degrees because that way, eventually, we'll get to the right orientation of the robot. We'll just like get we're just pretending the robot rotates instead of having to rotate the entire set of trees. Trees.begin, trees.end. Let's also sort the trees and the readings. Okay, so one thing that's interesting is if we sort the trees in lexicographic order and sort the readings in lexicographic order, if we assume that the correct orientation, then we don't have to do anything. We don't have to we don't have to do any computation. Sorry, they're always in the same order, and so we can just pick the. Sorry, what am I saying? If they're in sorted order, the sorted orders match, and so it's really easy to just do a pass through the trees and check if it matches, and try and generate the readings that it gets, and see if that matches our readings. So let's just do that. So first of all, we need a particular offset. So 4 int dx equals 4 int a equals 0 is trees nt pick the match for reading 0. Okay, so int dx 0. Okay, and dx equals trees of 0 minus reading 0, 0. dy is trees. Okay. Okay. Or this is trees int, yeah, so sure. We'll just call them these. Yeah, x and y. And dx and dy. Okay. So now for I equals j equals int readings size, auto is good equals dx dy. So by the way, there are no two trees at the same place, right? Hello. Hey, okay. Yes. So back to this. Okay. Let me check on something real quick. So the coaches meeting is going to be happening soon, but I think we can I think we will probably, let's stay on the contest. I think the coaches meeting is mostly for coaches. Okay, yeah, sorry. So here's this. So it is good. Yeah, I think coaches meeting, there's presenting some things, but you guys are probably more interested in the contest. So we'll stay on the contest. Yeah, forest for the trees. Let's see. Sorry, the main question is, are there ever never be the same location as a tree. Okay, so we have to go check. Sensor tells you relative to the front of the robot, unknown direction. You do have a map of all trees represented in X, Y. Okay, I'm going to assume that there are no two trees at the same place, and I'm also going to assume that there's no 0-0 pair. But yeah, we'll see. So tree equals 0, for I equals 0, I is less than t, I plus plus. Trees I0 dx dy if abs Rx abs Ry is greater than Rmax, and then we don't do anything, then it shouldn't be visible, and else j equals ns, return false, else if j equals ns or j equals ns or readings j not equals rx ry, and return false. Okay. Okay, so we check if these trees are good we just scan through the trees. If Rx equals 0 and Ry equals 0, return false. We're not allowed to be on top of a tree, and then we just need to check if this thing is good. So if is good, dx dy. Numsol 0, num array and 2 last sol. Minus 1. Okay. And then, yeah, so if is good, dx dy, numsol plus plus, last sol equals dx dy. So if num sol equals 0, impossible, else if num sol equals 1, sol 0, else. Okay, that should be it. Okay. So let's just test this real quick. Okay, cool. So yeah, let's go submit this. This is Forest for the Trees. No more Suica game. And yeah, let's see how this goes. Okay. Okay, cool. Fast. Great. Plenty fast. So pretty much you just brute force the last tree and then check if you brute force where which tree the first sensor reading corresponds to, and then you just check if it's good. You should be able to do this faster than this, but I'm not entirely sure. So yeah, but that's good enough. Okay, Cool. What other problems do we have? So I think we've solved A, B, C, D, F, I, K, which I think is all problems that have been solved in this contest. So now it might be time to just start reading problems. A, B, C, D, F, I, K. The scoreboard. Rutgers has an incorrect submission on J, so J is probably tractable. It's interesting that they haven't chosen to work on K. I wonder if they're not looking at the scoreboard as much as they should. For all the other teams, for all the other problems, it seems like teams are just kind of getting to the point where they've solved all doable problems. So they're solving all doable problems. Okay. B, C, D, F, I, K, that's 7 problems. So we have E, G, H, J, L. So let's look at J. J has a lot of submissions, but no one has gotten it correct. So that might mean it's hard, that might mean it's easy, we'll see. So it's an interactive problem, base high-low game. Okay, so for each problem you write that tries to figure out a number of up to 64 digits in a specific base. Okay, so the number of your guesses, floor log 2 base. Okay, so so when your program starts, it should read 2 numbers, the base and the number of test cases, which is the number of digits in the first test case, a D digit. Okay, so D digit string in base B, pretty much we're just running D. If the judge system does decide to cheat, it will cheat only once for a single digit. Okay. Okay, so if the value of the string is correct, you guess the number and you get it back. If the value of the string is incorrect, then a plus means that the digit in that position is too small, a minus means it's too big, and equal means it's correct. You will make a new guess based on the information you got back. You will repeat this process until you receive the correct message or the judge terminates because you took too many guesses. If at any point during the guessing dialogue you should send it back a line with the word cheater on it. If the judge system was in fact cheating, you will receive correct. If it was not cheating, your program will be terminated and you will receive a WA response. Respond in different ways to the same guess. So because you're allowed to just call him out on cheating, it seems like you should just be able to binary search on this and then get the answer. Let's think about it. They're only allowed to cheat once for a single digit. So it seems like what we can do is just binary search each digit independently, and then once each digit becomes correct, then we try and submit it, and then if he answers, we submit what we think is entirely correct, and then if he doesn't mark it as correct, then we can call him a cheater. It's interesting, like a lot of teams have this wrong, and it probably means that they missed a case or they missed something. This does seem like a pretty tricky thing to implement, and it's also not on Caddis. So I think I'm not going to implement this problem because I won't be able to tell if I have it more correct than the teams or not. So let's just move on and read the next problem. So L also has a submit. I don't know if it was a good team. Okay, so make your own Morse code palindrome. A palindrome, Morse code, palindrome, takes an input string and determines the smallest number of characters to append to the end of the word to make it a Morse code palindrome. So you're given a prefix, and then you need to make it a Morse code palindrome. Okay, well, this is like a pretty, like, what is it? This is like a pretty interesting problem. in general, like pretty much we should just need to DP. So because Morse code, like the length of Morse code is not too long, right? So each digit. Sorry, how do we talk about this? So the idea of like how to make this palindrome is we're just going to consider like sweeping the. Just consider trying to check if the number is a palindrome, if the string is a palindrome. So you just like go from the first character and then you look at all its Morse. You convert it to Morse, and then you just take the first Morse symbol in each direction every time, right? And at any point, like you only have like a couple symbols, a couple symbols which like could be the same. At the same time, Morse code is very permissive. So we're trying to append the smallest number of characters to the end of this word, the end of the string, which is not the same as like, it's a bit strange. Input consists of a single line of up to 30 capital letters and or digits excluding spaces or punctuation. So you should just be able to do it with like DP kind of thing. Kevin is telling me something about this problem. Okay, no, he's telling me about a different problem. Okay, so Morse code palindrome. Morse code for the letters and digits reads the same forwards and backwards. Okay, so let's think it through. Yeah, so another thing about Morse code that's worth noting is it doesn't quite contain all length 3 and length 4 strings. It contains, I think it contains all length 3 strings, and it does not contain all length 4 strings, which is pretty silly. And it contains all length 1, 2, and 3 strings, and also a bunch of these length 5 strings. So pretty much, I think the general idea is you want to write this as like a DP, where it's like you have some partial you have some Morse string that you want to make into a palindrome, and then it doesn't. The inputs might as well just be like empty. It might as well just be empty or something. But pretty much what you do is you append a matching string at the end, and then you cancel out everything. And then now you have a smaller DP, and then you append, and then now you have a smaller DP. And so, and once you like append past the end of your string, then it becomes like, sorry, what is it? Then you have to, then you start prepending characters to the middle part of the palindrome. And so you can kind of do that. So you stop when either like the fixed string is a palindrome or you appended enough. So that's kind of annoying to implement, but it is like, it's not too bad. It does seem like there's a lot of edge cases, which might be why not many teams have solved it. Let's just finish reading the problems. There's E, G, and H. So E looks pretty awful. We have 3 spheres and a tetrahedron. So tetrahedron. Sorry, what problems are, what are the rest of the shared problems? Okay, so is palindrome one? No. So the only thing that's shared are G and H both shared? Okay, let's go read G and H. Pearls is shared, and then H is a fast walk in the woods, which is also shared. So there are 2 more shared problems, and let's just finish those. It seems like the shared problems might be all the easy problems, and so we can just, let's just see if we can clean those up. So G and H, G is pearls. Nicolay's jewelry store in Puzzletown sells a set of necklaces. Oh, let's read H. H has a submit. Okay, fast walk in the woods. We have orthogonal woods. The paths are laid out on an orthogonal grid. If there are 3 branches, he takes the middle one. Two or more paths. If there are 3 remaining branches, this is jog and walks to the nearest exit. he assigns each path an interest value. The higher the value. Okay, so remaining is because after the number of paths is you know, if you delete too many paths, then after the nth pass, the path will cease to exist as far as Bryce is concerned. And so any 2-branch intersection becomes a 1-branch intersection, and so on. Okay. Okay, so if there are 2 remaining branches, he takes the left one. Okay. So he enters the park in an intersection. Okay, so let's see. Let's think about how to do this. So the main idea is we kind of just continue. When an edge disappears, the edge disappears like for good, right? The number of times an edge can disappear is not too large, right? It's at most like 10 to the 5 or something. Or sorry, it's at most the number of edges, and the number of edges in a graph with average degree at most 4 is at most 2 times n. So it's at most 25,000, like it's at most like 5,000 edges. And so for each edge, right, we can kind of just keep running until we delete an edge. Like that's always a safe way to. That's kind of always a safe way to execute this. And what we can do is when we start running, we run along some way, and then eventually we reach a cycle. And so once we reach a cycle, then we keep looping around in that cycle. And so we can just find the first time that we delete an edge because it's in the cycle, and then like which would just be the smallest edge in the cycle, and then like essentially very quickly just remove everything down in that cycle. And we can do this in linear time, so that's pretty like we don't have to do any fast data structures or anything to make this efficient. So we can just kind of keep simulating this over and over. So we just start walking forward. Until we reach a cycle, and then we process the cycle. We process the cycle efficiently based on just what's the first path in the cycle that we would delete, and then we just continue from our new starting point. The main thing to note is like the main reason this works is because pretty much for every edge, or maybe for every like directed edge, we must follow it. Yeah, for every directed edge, we always just follow it to its end. I guess one question I have is, will we ever loop back on an edge? And I think the answer is, like, will we ever cycle through this edge multiple times? And the answer is we could. Like we could use the same edge multiple times in our initial cycle, and so I think we still just process it's harder because now each edge could be used up to 2 times in the cycle. Like we go forward and then backwards, and then those are essentially distinct, but we can still process those kind of efficiently enough. Okay, so that's pretty interesting. It's kind of pretty implementation heavy, and just got to deal with that kind of edge case. And then problem G is pearls. Sells a lot of necklaces consisting of black and white pearls, firmly glued to a cord of length K. Masu. Okay, so this is a puzzle, logic puzzle called Masu. You have a single loop through all pearls, and through every black pearl, you have to go 2 straight in 2 different directions, and then through every white pearl, you have to go straight and then turn on one side. And so what we're given is a spacing matching the cells on the surface. Okay, so we're given a string, the number of rows and columns, but because black pearls are more desirable than white ones, there'd be at least twice as many black pearls as white ones. No two pearls are ever separated by a gap of empty core longer than 5 units. 5 is kind of long, though. Does any team have a solve on this? Okay. Black pearls are more desirable. Twice as many black pearls as white pearls. Pearls displayed at a value line surface. Connecting some of the cells on display. So there are twice as many black pearls as white ones. And then it must, I assume that it must just loop back directly. Okay. The upper left is 1. The length of the chord. String consists of a string K. Okay, will always be a pearl. And then the row, you're given the location of the first thing. So it seems like you should kind of just brute force. Like the grid is not very large and you don't have too many options, but there are kind of a lot of ways of turning things and stuff. So, this is very interesting. I feel like it should be kind of brute force, but I don't really have a good, I don't even know how you would do that. This is interesting. Seems pretty tricky. Half of the network's length consists of pearls rather than empty sections of cord. Oh, at least half of the necklace is pearls. At least 2/3 of the pearls are black, which means that at least 1/3 of the necklace is black pearls. At least 1/3 is black pearls. And you can't have 2 black pearls next to each other. And so there's always a gap of size exactly 1, right? Isn't that how it works? Sorry, sorry, never mind. Yeah, you can't have 2 black pearls next to each other. And so, what happens now? If 2/3 of the path is turning, then you can have some straight sections, but you can't have too many straight sections. So, let's see. At least 1/3 of the necklace is black pearls. That's like very dense, but at the same time not quite enough to be like anything provable. It's very interesting still. J just got solved. Okay. So that must mean that someone like figured out their bugs and stuff. That's good. That's Cornell Kappa. So they're actually in the lead by problems now because Rutgers has not solved K. Okay. Okay, let's go read the rest of the last problem. We read all problems and thought a little bit about them thought a little bit about all of them except E at this point. E is, you have a sphere inscribed in the tetrahedron tangent to tetrahedron OABC. There's a sphere inscribed in the tetrahedron tangent to the inside of each face, OA, OB. Okay. Second sphere tangent to the extended inside and to the outside. Okay, so this is a in sphere and an X sphere. If you know like triangle geometry, this is, this is like a in circle and an X circle. Okay. There's a third larger sphere which passes through the vertices A, B, and C and is tangent to each through A, B, and C and is tangent to each of S1 and S2. So the outside of the smaller spheres that is tangent to okay. Interesting. Write a program that takes as input the vertices O, A, B, and C and computes the center and radius of the big sphere. Interesting. Okay, so here's how you compute the small spheres. So the small spheres, pretty much, if a sphere is tangent to two planes, then it has to lie on, then its center has to lie on the the 3D angle bisector of the two planes. So if the two planes are like this, and the sphere is tangent to both of them, then the center must lie on like the plane which bisects this angle. And so you can take these three angle bisectors, and the angle bisectors through like the angles through the planes of OAB, like of OAB and OAC, and then you take those angle bisectors and that gives you a plane, and then you intersect that with another plane and then you get a line, right? And so you get these lines, you get this one line that the center of the green and red circle each pass through. If the circle so also there's this sphere that is and so pretty much there's just like some scaling of the sphere where it's tangent to the BAC plane, and it's you scale. Sorry, the center just like moves away, and then it like has to be tangent to the BAC sphere, a BAC plane. The other thing, if you consider the BAC plane, because the large circle, because the blue sphere passes through B, A, and C, then the center must be like on top of the circumcenter of ABC. Because if you consider the slice of the big sphere, of the blue sphere with the ABC plane, that forms a circle, right? And that circle must be the circumcircle of ABC. And so that must just be the circle. And so the center of the sphere must be like kind of above this circumcircle plane. And then let's see what happens. So now it needs to be tangent to both the red sphere and the green sphere. But that we can just, like, now it's a one coordinate problem, so we could just like, we could just solve that. I don't know why it would be tangent to all of them. Like 3 points and 1 sphere already determines a sphere. So I don't know why you would need the blue sphere. Maybe it's just to disambiguate, but it is kind of interesting and surprising to me that that this blue sphere is tangent to both the inside and the outside. Yeah. That is a little surprising to me. But that's how you would solve this problem, I think. Yeah, that sounds like the right way to solve this problem. You can also do this algebraically. Like there's point line distance formulas, and so if you just like set the point line distance from OAB to like from the center of the red sphere to OAB and the center of the red sphere to OAC to be the same, then that actually gives you the same plane that I was talking about, and so you can from there you can go grab your once you have that, you can find the coordinates of the center of the red one, and then you can do all the symmetric computations. Yeah, it seems kind of tricky, but I guess it's doable. Yeah, that's pretty interesting. I kind of wonder if maybe the center of the blue sphere is just on the line between the centers of the red and the green, but that doesn't sound right. So yeah, I don't know why it's the same distance. That's pretty surprising to me. I don't know if anyone else is better at 3D geometry than me and can answer that question. But yeah, okay. So that's all the problems. I'm going to take a quick break. We can also take a quick look at the problems here. B is an easy problem that's not shared. D is D looks hard. H, D, H, B, D, H, K are the non-shared problems. So we could take a look at those. But I'll do that in a bit. So yeah, thank you guys for watching. I will be back in a second. Hello, I'm just checking in real quick, just taking another look at the scoreboard. So it looks like, yeah, so the stats are looking pretty good. We have, let me go, okay, we have 2 teams with 7 now. They have 7 by solving all the main problems, and then each one of J and L. Rutgers has 6. They really should solve K. I mean, I don't know if they're not looking at the scoreboard or what, but they really should, get that. And then they need to just finish, and then they have F. But yeah, we're starting to see submissions for J and L. Just a reminder that J is the guessing game, but the thing can lie to you, and you can call him out for cheating. So I think you can just keep guessing until it seems wrong, and then print something out. And then L is the palindrome problem, which is like a DP, and that one is pretty tricky. But yeah, so we're still watching. It looks like the scoreboard is a little messed up because of the standing, so let me go try and fix that. How do I do this? Start from row 1, show up to 5 rows. I don't know what's wrong with this. I guess we'll just leave it as is then. I like the stats, but yeah, I don't know how to show the teams. I don't know how to truncate the scoreboard so that you can see it over the stats. Does the scoreboard contain stats? It doesn't. That's a little unfortunate, but sure, we'll just leave the scoreboard out. Okay, so we'll just leave it at this for now. But yeah, looks like teams are starting to get problems, starting to get J and L. I think G is. I think H is pretty doable. H is the walk in the woods problem, and then beyond that, some teams might attempt E. E looks like a problem that, if you have time, you should probably solve. You should probably have one person writing out formulas on paper right now, and once you've written down the formulas, then you just need to put the formulas into the computer, and that's really easy. So E seems like it should be solvable, but yeah, the rest of them, we'll have to keep watching. Yeah. Okay. Cool. I am going to go grab lunch or something, and yeah, I'll be back. I'll check in another little bit. Hey, so there's some talks going on for coaches right now, so I'm actually going to broadcast those for a bit.
What I'm going to do is like a proof by contradiction. Okay, so I'm going to assume I have an algorithm for the disjoint sets problem that runs in this faster time, and I'm going to use it to solve CNF-SAT in faster than 2 to the m time. So this will contradict the assumption that I just made that this is impossible. Okay. Let's see how to do it. So I'm gonna assume, again, I'm assuming I have an algorithm for disjoint sets, and I'm now gonna give you an algorithm for SAT. Okay, here's how it works. So let phi be the input formula. So it's a formula on m variables and polynomial and m clauses. The first step, this is a step that actually shows up in a lot of algorithms for SAT solving, is we're going to partition up the variables into 2 sets. So like I'll let S1 be the first set of variables, the first m over 2 variables, and S2 be the second m over 2 variables. And now I'm going to think about partial assignments where we assign to true or false just the variables in S1, but not the variables in S2. Okay, so I'm going to call this a partial assignment because it's assigning to true and false just the first m over 2 variables, but not the second m over 2 variables. So let alpha be one of these partial assignments to just the variables in S1. So the main observation is that for a given clause in the formula, this partial assignment may or may not already satisfy the clause. So let me give you some examples. So okay, here's an example of a clause with 4 literals in it. And let's say alpha is a partial assignment that maps x1 to false and x2 to true, but it doesn't say anything about these other 2 literals over here. So if alpha is this partial assignment, then alpha already satisfies this clause. Since it's put x2 to true and x2 is part of the clause, then if we know if alpha is this assignment to S1, then this clause is already satisfied regardless of what's happening in S2. But on the other hand, here's the same clause, but now maybe alpha maps both x1 and x2 to false. Now, alpha doesn't satisfy any of the literals in C, so we don't yet know if C is satisfied for a given full assignment. It depends on what the assignment to the variables in S2 is. Okay. So here's the set that I'm going to solve the disjoint sets problem on. I'm going to, for this partial assignment alpha, I'm going to let x alpha be the set of clauses that alpha does not satisfy on its own. Okay, like the set of clauses that are like the second case and not like this first case. And similarly, if beta is a partial assignment to S2, I'll let y beta be the set of clauses that beta does not satisfy on its own. So now, if the intersection of the set x alpha and y beta is exactly the set of clauses that neither alpha nor beta satisfies on its own, and therefore that when you pick these 2 assignments, the clauses that are not satisfied. So the intersection between 2 of these sets will be the empty set if and only if alpha and beta together form a full assignment to the formula that satisfies the assignment. So by making these sets, we've exactly reduced from SAT to this disjoint sets algorithm. We form these sets, and we now want to figure out, is there a pair of disjoint sets, which tells us that all the clauses are satisfied. Okay, so just to summarize, our algorithm, given this input, this formula phi, for each partial assignment to S1, it makes a set X alpha. For each partial assignment beta to S2, it makes a set Y beta. And then it uses the disjoint sets algorithm to figure out if there are alpha and beta such that these two sets are disjoint, which means that these two partial assignments satisfy the formula. That's the algorithm. So the running time to solve SAT now is just the running time to solve disjoint sets where, well, how many sets are there? There's 2 to the m sets. 2 to the m over 2 sets. Like each partial assignment is an assignment of true or false for m over 2 variables. So there's 2 to the m over 2 choices for each of the partial assignments. So there's 2 to the m over 2 sets. And what's the size of the universe? Well, it's the number of clauses, which is poly m, which is poly log n. Because these are sets of clauses. Okay, so we assume that we have an algorithm for disjoint sets that runs in n to the 1.99 times d to the 100 time. And so plugging these in, we now get a SAT algorithm that runs in 2 to the m over 2 to the 1.99 times poly log n to the 100. And you check, 1.99 over 2 is less than 0.999. So this is a 2 to the 0.999 times n time algorithm. So this finishes the proof of the theorem, and it shows that if we had a faster disjoint sets algorithm, we could use it to get a faster SAT algorithm. Okay, this is my last slide. So what you might ask, what does this mean? Okay, so we showed that a faster disjoint sets algorithm than the kind of straightforward algorithm would refute the strong exponential time hypothesis. But strong exponential time hypothesis, it's like we already don't know how to prove P is not equal to NP. Strong exponential time hypothesis is an even stronger assumption than this. Like it's possible that P is not equal to NP, but strong exponential time hypothesis is still false. Okay, so is this a reasonable thing to assume? And it's actually many but not all complexity theorists do believe strong ETH. There are some prominent complexity theorists who do not think it's true. But nonetheless, proving this, I think, is very exciting because it shows, okay, maybe this doesn't 100% convince you that there's no better algorithm for disjoint sets, but it does mean that if you come up with a better algorithm for disjoint sets, that would imply also a better algorithm than anybody knows for SAT. So it would mean that there's this SAT problem that is very, very well studied. Lots of people have spent a lot of time trying to come up with algorithms. And it would say that if you come up with a better algorithm for disjoint sets, you would at least be improving on the algorithms of all these other people. So it's kind of a win-win, I think. It's saying either disjoint sets really is hard, which is what you set out to prove, or you get a breakthrough in solving SAT. Yeah, and certainly solving SAT faster is also okay. And just to conclude, so this is one example of a type of result people prove in this area of fine-grained complexity theory. So it often studies assumptions like the strong exponential time hypothesis and reductions, where you show that assuming it's true that some other problem is hard. Yeah, exactly. So you show that if you can speed up the best algorithm for some problem you're interested in, like disjoint sets, then it would also give a speed up for a fundamental, like very well-studied algorithms problem. Like SAT is maybe the biggest, but other ones like APSP and free sum are also well-studied problems we've probably seen before and thought a lot about it. We kind of assume it's not possible to further speed up our algorithms for these problems. So if you show hardness from one of these assumptions, it at least gives evidence that no improvement is possible for your problem, or at least if your teacher asks, or your boss asks you, why don't you have a faster algorithm for this? You can say, well, many algorithms researchers have tried and failed, so it's not my fault. Okay, that's all I have to say. Yeah, thanks.
Any questions for Josh? I guess as we set up the next talk.
I guess there's one on
Okay, cool, thanks, John. Alright, so with that, actually, Zoe, are you ready to speak right now?
Yes.
Okay, and also, yeah, if you can have the camera on, and then I'll pause the sharing and then you can share your slide. Let me know if you cannot somehow share the slide.
Yes, I think I can. Let me see which is
Christian, I just had one quick question. Yeah, this week. So is the fine grained, is it basically they're trying to find some sense of the complexity of the intermediate steps, the intermediate cases in a problem like this?
Yeah, exactly.
Got it.
So there are like lots of different problems we can reduce SAT to. Then we can kind of say SAT is the fundamental reason why these other problems are hard.
Well, that's right. I just did that there's some partial, there's some partial embedding problems in block design that behave that way.
Oh, yeah.
Thanks, Bill, and I guess Josh again. And then with this, so if you'd like to, I guess, introduce yourself and then start the conversation, that'll be good.
Yes. Hi, everyone. I'm Joe. I'm an associate professor at computer science at Columbia. Yoan and I have a startup together that is working on using conversational AI to support code learnings, interview trainings, and so on. So that basically you have a conversational similar to ChatGPT, gives you hints or simulates how a interview works. Like basically, interviewer is the chatbot, and you are coding, and then also answering questions or ask clarification questions to your interviewers, which is a bot that we've tried to simulate. So today I'm just going to talk a little bit about, as it's an introduction talk, that it talks a little bit about why the large language models are so much better than before, most of the algorithms before, and what are the sort of use cases that it is in conversations. One of the biggest reasons that ChatGPT or GPT-3 that is so popular is really coming down that the previous pipeline for natural language processing is you train a model for a specific domain through a fine-tuning process. Usually it's a supervised task, which means that you have to have a model that is specifically created for a task, which requires a large number of supervised data, which means that you have to collect utterances. For example, you want to build a sentiment detector for movie reviews. You have to collect all these movie reviews and ask humans to label these movie reviews with labels, positive or negative, and then you can train a model on top of it. And usually when you train this model, it's very difficult to generalize to other domains. So if it's a sentiment classifier for movie reviews, it's hard to generalize it to for example, hotel reviews, or even harder, like a news, like a sentiment classifiers, because the models may learn not only the content, but sometimes they can also exploit spurious correlations with respect to the data set it was trained on. So basically, if you remember from machine learning assumptions, your training data distribution has to be similar to a test data distribution. But in reality, when you're collecting your training set, very likely your distribution doesn't follow up with the realistic, like a deployment environment. So this is all these problems that we have with previous machine learning or NLP pipelines. So why GPT-3 or GPT-4, these large language models are slightly different, which is really coming down to, instead of collecting 1,000 examples and training it for a specific task, we wanted the model to learn information similar to how humans learn things through demonstrations and instructions. We would train a general purpose model through teaching the model various different tasks through a pre-training process and instruction tuning process, so that the success point is really that the model is so large that it's really a lot of parameters, 175 billion parameters. There's a certain sort of like a flip in terms of increasing the quantity of the parameters, that the capability of the model reached a gap in terms of performance on on-scene tasks. So because of the GPU resources, and because of a lot of pipelines that we built over time, we're able to train these models that like scale up to 175 billion. So how do we actually train these models? This is as simple as a very original idea about predicting next token. So we say a word is defined by its neighbors. So the language model, by definition, that we have been working on for the entire a couple decades is about how do you predict the next word. For example, I'll give you a sentence: the cat sat on the what. So predicting the next word really help you to understand a lot of information just through a simple task, predict the next word. So if you have seen enough corpus, so this corpus doesn't really require annotation, you just can crawl information online or everywhere. So we definitely see among all these informations, the cat sat on the mat is more likely to happen than the cat sat on the mat, right? These kind of frequency of probabilities taught you grammar, right? And then this sort of like frequency also is going to teach you word knowledge. The cat sat on the mat is more likely to be used as Will sat on the mat, and teach you different scales. 2 + 2 equals more likely to follow with a 4 instead of 5. Teaches you on specific downstream tasks like sentiment analysis. That movie was terrible. I'd give it more likely to be 1 star than 5 star in terms of conditional probability. So that's right. Really, we are using a transformer-based model that has multiple layers. We're feeding these models with all these kind of tokens that predict the next word. The language model, by definition, is really as simple as the distribution over target words given the previous history. So this is a language model's parameter, theta. And then given the previous tokens that you've seen in this word, in the sentence, we wanted to predict what's the following one, UI, after UI minus 1. So the probability is really coming down that once you generate the UI and you patch it in as a sequence, and then you generate UI plus 1. So we call it autoregressive generation. So this is how GPT-4 generate the next token over time. So the quality of these language model really hinges on what are the data set it has seen before. So where do you usually get data set? Common crawl is basically you crawl online to get all the information about the web. And the web text 2 is doing a little bit more of fine-grained filterings. And books 1 and books 2 are books that people wrote like these over so many years. Wikipedia is things that we usually look for factual information. So for these data sets, we always want to prioritize the high quality data set compared to the low quality data set. So web text 2 was more fine-grained filterings. Wikipedia was very fine-grained curations, or usually have much higher weights than like Common Crawl, which has a lot of like noises in terms of HTML tags and so on. And then once we train these models, of course, this is a simplified version about like predict next word token and pre-training. There are a lot of details about how do you optimize this, how do you curate data, and so on. But the general idea is still just predict the next word to do pre-training, and then do a fine-tuning process to give it different tasks so they have seen different tasks, so it will learn these kind of general capability. So once you have a large language model, how do you use it? So this is like sort of new category of like utility called prompting. So you can give it an instruction of the model. So basically you type in the sentence in your ChatGPT or GPT-4 and you get an answer, right? So what we call zero shot is you don't give it any example, just give it an instruction and the input, which is your X. PDAEF equals is your X, and then you hit enter, they give you a Y, which is the next token it predicts to follow this instruction. So the instruction unscramble the letters into a word and write that word. For example, this could be defeat. And one shot is you give it an example, so the model learns the logic through examples along with the instruction. So for example, this one can reshuffle into reciprocal. Few shot is like you give it more than one, couple of more, and then you get better. So ideally is that you don't have to retrain or fine tune the model anymore. if you for reality, some of the tasks on sentiment, give it a 0-shot setting is good enough. But if you have a specific task that is slightly different from general tasks that people are trained on, you give it some example, you usually get better results. So the model is fine-tuned on various instruction tuned on different tasks that are created over years. So for example, completing stories, common sense reasonings, trivia style questioning, inference task, natural language inference task, translation task, all these synthetic tasks that we can create automatically through scripting. So the idea is still, if the model have seen similar tasks, you can do better. So for example, as a trivial task, trivial question and answering data, there are questions like Nude Descending a Staircase is perhaps the most famous painting by which 20th century artist, right? So the ideal response for this is Picasso. So if we give it no examples and just ask this question and use a model that is 175 billion, which is GPT-3, right? You can actually, it's the blue line, which you can do actually 65%. While previously, if you collect 1,000 samples and fine-tune a bird-based model, you usually get, for example, a little bit less than 70%, which is very little gap. And if we give a GPT-3 model one-shot example, you perform as well as the fine-tuned model before. And then if we give them 64 examples concatenated through the prompts, basically your instructions, you do even better than them. And of course, the scale really matters. From 13B to 175B has a huge difference in terms of gain. And it's really coming from, it doesn't really work that way, but it's almost working, and it's working better than carefully created data sets. But of course, trivial data set, trivial QA is very similar to a lot of data set that the original pre-trained model has. For example, this natural QA, web QA, trivial QA is similar to this particular data that we would give it. But what if the task is slightly different? Has some trick questions that's sort of different, then the sort of like a performance really degrades. So this is already telling you that the limitation is if your task is similar to the general NLP test that the model has seen, you're actually get better results, otherwise you don't. For example, ANLI is called adversarial natural language inference task. So the context usually has like twists in it. So for example, we shut the loophole, which as American workers actually subsidizing the loss of their own job. They just passed an expansion of that loophole in the last few days. 43 billion of giveaways, including favors to the oil and gas industry and the people importing, selling fans from China. So the question is, the loophole is now gone. Is it true, false, or neither? Because there is some, like a lot of these kind of back and forth information. The correct information is false. Because they haven't patched out the loophole at the moment, but it's very different from a lot of these kind of like more straightforward tasks. So that's why a fine-tuned task on similar fashions gets you better performance compared to 0-shot, or even like K equals to 50-50 shot in context tuning results. So of course, we still see like given 50 examples and one example is a huge gap as well. In general, if you give it a prompting-based model, give it more examples, you always do better. So why is ChatGPT so popular compared to GPT 3.5 and 3 before? It's really coming down and it's accessible by everyone, and it makes the context window longer. That's why you can back and forth have conversations. And then there's a lot of like underlying techniques that we made it. OpenAI made it possible. For example, they include human in the loop to do we call RLHF, reinforcement learning with human in the loop, to improve the model's performance over time. So ChatGPT before a certain time was learning upvotes and downvotes of their real users, so that it's more aligned with the user's preference over time. So ChatGPT really doesn't come with a manual. That also makes it sensation, because people can test it on all the problems they wanted to answer their everyday, like in their everyday life or workflows. So that's why people are talking about what ChatGPT can do or cannot do on social media. You get a lot of retweets if you find a stupid error that ChatGPT makes. So this is really coming down that people find like ChatGPT can be extremely smart at certain cases and tasks, but extremely stupid at certain other tasks. This is really because the model, it was trained on next word prediction, trained on curated sets of data, which is especially for certain purposes. That's why it's not well calibrated with human general intelligence. Think about it, the model can do translation pretty well. No adults like in certain parts can do all these kind of different language translation that well. But sometimes like if it's just a logic question, most people can do it. But ChatGPT sometimes still makes error in simple logics. But people have been using it for compiler, interactive debugging, writing marketing content, using a writing assistant to write emails, to write essays, and so on. So people have been using it for other things like making summarization, making security loophole checkings, using it as a vector database to do retrievals, and so on. But in general, ChatGPT is really popular because people are really looking at on the tasks that they really care about. So they can create targeted examples, put into their prompts, or explain the instruction really well, so that they can iteratively refine their instruction over time to build these build applications. With like ChatGPT plugin, there's more and more things you can do by calling the API to get some intermediate, like more structured information to like process. But overall, like people say, oh, is ChatGPT a 2-year-old? I always said, not really. I have a 2-year-old. It can do a lot of things really nice, but nicely the ChatGPT can do. For example, follow instructions to throw a banana peel in the garbage, but ChatGPT can't do any of these kind of actuations or plannings very well. But nowadays, like we really do see like there are tasks that they are not doing well. For example, they still have hallucinated information that was never told. There are a lot of work we do in terms of how to reduce hallucination and biases. Biases is really coming from intrinsic because the model is learning from massive corpus. There's no supervision of what is correct or what is incorrect. So it's basically learning from like what majority people say. So that's why you also amplify the bias over time, because the majority is all on certain opinions could be biased. So we definitely see like we're getting more and more parameter-based models, and we're getting more and more training tokens. Now this is number 10,000 billions of tokens that they train on these kind of really large model. But in general, it's like the bigger the model, the more data set you need to fine tune it to buff up the capacity of the model. We definitely do see that making ChatGPT into a product that people can actually improve their daily activities, productivities, or other tasks is still very difficult. For example, we have seen like if ChatGPT is incorporated with Google, for example, this is what Bing did, right? But if we suppose that it works with Google, we also have to look at what are the possibilities that we refine the technology into a product, and what are the back-end work that we can do to reduce the cost. For example, we take Google as an example in terms of search, right? So they're really coming down to revenue per query. We say like a per query, per search that you do, Google gets some money from the advertiser on average. And there's a cost about like a kind of infrastructure costs and so on. And then so basically your income is the difference between the revenue and the cost. And then we look at how many seconds there are queries coming in. For example, we think 320K. So your annual revenue is really just a query per second multiplied by revenue per query. And then your annual cost is the same, it's similar. And then you really want to look at the operational income, which is the difference between the revenue and cost, right? So originally it was 55 billion. And if you want to add ChatGPT, your cost increases per query because you have to use GPT to generate things, right? And then you have like additional cost over 35.9 billion. Your revenue really cut into a third of it. This is really hard to justify to your manager that we gotta get ChatGPT into your Google because it really is slashing your revenue. But it really coming down to ChatGPT have very long content history. For example, they can do 32K. But when you do search, you don't type in an essay into a search bar. You just search by keywords. That's why you can limit the context window to only 350K, and it can cover 99.99 in terms of keyword search queries. Now you can reduce your cost to 6.3 billion. Now you're back up to almost 50 billion in operating income. Again, there is also, we know the long tail issues. The 20% of the frequently searched and keywords or queries we usually call covers 80% or 90% of what people are usually in total queries, because people like to ask similar things, right? So that if you catch the top 20%, it reduces, it brings back your operating income above to 50. And when we know, like we're Google, for example, we can even make changes in terms of hardware. So TPU is a type of GPU that is specifically designed for AI. So that's why you can utilize this, even further reduce your operating cost to 52. Now you're really coming down to see the cost analysis and product designs in terms of how to convert technology into product. That's just an idea, but really coming down is if we incorporate GPT-4 inside of the Google search, does the query per second increase? Right? If it doesn't increase, you're basically using the cost to gain no revenue back, right? But at the same time, like for Google, it's a complicated decision process in terms of like your safeties and customer brandings and so on. Coming back to like we talk about GPT-4 plugins. It's really like if the general model is not good at certain things, you can always ask for help by bringing these kind of API tools. You can call mass calculator. You can call QA models that are specifically trained on data sets to help you to incorporate APIs over time. But in general, we really do see like large language model is a very dynamic environment. We have seen a lot of these kind of evolutions from 2018 and so on. So here we specifically mark that the shaded one is open source, and then the empty ones are closed source. So we've seen like over time, the GPT categories like are all like your friend GPT-3 on. Most of the ChatGPT, GPT-4 are more closed source. But GPT-2 was originally open source, right? Because like you become more and more productized, like you're more and more likely to not share the information about how you build things. So recently we've seen Google was originally all very open source oriented, but they started to also make their like newer models more private over time. But for example, there are exceptions like Meta specifically created a Llama type of a model. Now, the best open source model or large language model that is available is Llama 2. And Llama 2 come in different sizes, 7 billion, 13 billion, 70 billion, so wow. So usually we see like 13 billion Llama 2 model would always be a good recommendation if you want to do fine tuning or try out on your open source pipelines. But in general, the future goal is really how do we teach ChatGPT to do things that an expert are really good at? So for example, how do you apply domain information into it? How do you get more privacy preserving information? For example, you and I are building specific for education process. How do we make a ChatGPT more aware of what is a good way to teach students? What is when to give hints? How to give hints in a way that is useful, constructive to the user? How to give feedback in terms of to the students in terms of helping them to correct the code or help them to navigate the problem-solving the dynamics in order to make it efficient, less intimidating over time. I think I'll just stop here and take questions.
I don't know whether you knew, but at the at the World Finals, once we reschedule it, Jacob Pachochi who is the lead developer of ChatGPT 4 is going to provide a alumni talk and yeah, and he was a two-time world finalist
Wow, that's really cool.
from Warsaw University. So y'all lead the charge.
Any questions before we move on to the next session? Okay, thanks everyone for coming. If you're interested to know more and seeing like what these LM models could be helpful for your use case, happy to talk more in the future.
Hey, okay, I think that's most of the talks. I don't think there's any more. We have just a half hour left in the contest, so what is going on? It looks like top teams are going to end up with 7 or 8 problems, probably all of ABCD, IK, and then, you know, 2 like most of FJL, and then possibly H. We saw one submit on G. It's not clear if that was by the Yale team. We'll see if they manage to pass that. But yeah, the scoreboard has already been frozen, so we can no longer. So we don't know if teams are like if teams pass their problems or not. We can get some guesses. It looks like Cornell has stopped submitting on H, I think. So they might have gotten it. And then I can't really tell about anyone else. Yeah. Looks like things are just, teams are kind of just finishing up their submits. Top team, yeah. I feel like 10, Cornell having 10 and winning is probably what's gonna happen here. And then we'll see where exactly the qualification cutoff looks. It looks like Cornell, here, let me share this screen. Yeah, looks like right now we have Cornell in the lead, Cornell, Princeton, NYU, Yale, Rutgers, SBU, and then maybe Columbia. Those are the top teams. It's pretty impressive how few schools are in the top 12. There's like 1, 2, 3, 4, 5, 6, 7 schools in the top 12. And yeah, so we'll see if Columbia makes it. But yeah, oh, sorry, let me turn music down. I didn't realize, has music been playing this whole time? Oops. But yeah, yeah, okay, we'll see. We'll see how much this scoreboard changes afterwards. But it is probably pretty much fixed. Yeah, so just a half hour left, and yeah, we'll see what problems stream in. Taking a quick peek at Nina. The Nina scoreboard is pretty impressive. It looks like a lot of teams have a pretty similar score. There were, I think, all the easy problems from this contest, A, B, C, D, F, I, were on their contest, and then also, IK were on their contest, and then also B was an easy problem. So there were kind of 7 easy problems, and the good teams should have gotten like 1 or 2 more problems on top of that. Yeah, I think H was tractable, and so yeah. Yeah, so yeah, on that side, one of the MIT teams has finished all problems except D, and everyone else is kind of struggling to clean up the rest of their problems. So yeah, cool. I think just go back and let you guys watch the rest of this. I think we'll be broadcasting the closing ceremony when we get there, whenever it starts. But until then, just sit tight. Yo, back again. Let's take one more look. Something's off with the scoreboard. Oh, we still have half an hour left. Okay, so there's still a bunch of the contest left. We're still just seeing submissions coming in. Princeton has more solves. NYU, Yale. These are all kind of safe schools. I think the interesting schools are going to be like this eighth place to 13th place range, because we'll probably get like Cornell, Princeton, NYU, and Yale will probably all make NAC, and the question is how many of Rutgers, SBU is Stony Brook, I think, and then Columbia maybe are going to make it. So that'll be pretty interesting to see. It looks like, there's at least one Rutgers team is claiming, has submitted to 8, optimistically has 8. Stony Brook team also optimistically has 8, and then Columbia optimistically has 7. So it's like pretty tight for Columbia. We'll see how they go. But NYU, Yale, and Princeton hopefully each have at least 8 or 9, and so they seem pretty safely in the lead. But yeah, Cornell, NYU, and then yeah, the next school down is NJIT, and I'm guessing they probably won't be able to. They probably won't qualify for NAC. So yeah, see how this Columbia team does. Also looking at the bottom of the scoreboard, it looks like we have pretty much all teams with at least one solve. We have almost all teams have solved A, with the exception of like 7 of them. And so that's pretty good statistics. Usually you want all teams to solve one problem and then, like almost all teams to solve another, but it doesn't look like any problem has that many solves. But at least almost all teams have a positive score. Yeah. Don't know if some teams maybe just didn't show up today. There are some teams with no submits, so maybe they just didn't show up, and that's fine. Looking over at Nina, it's not really any changes. I guess another MIT team has claimed 9 solves. Has claimed 11 solves, and then no one else is super close yet. And I think ECNA is going to be ECNA's scores. It's Waterloo and then Ohio State. I've never seen Ohio State on these. I've never noticed Ohio State on these leaderboards before, so that's pretty cool. Usually the top teams are Waterloo, and then CMU and CMU. But in this case, there's Ohio State and Miami and U of T up all in the top 5. So that's pretty impressive, and we'll see how they manage to finish it out. I don't recognize these names. Yeah, pretty cool. We'll see how the last bit of this contest shakes up. I think Nina has, let's see. I think Nina has 15 minutes to go. Nina ECNA have 15 minutes to go, and our contest has 25 to go. Columbia Blitzkrieg is spam submitting K in the queue. You can see that. I don't know if that's going to accomplish anything. I wonder why they're submitting so many times. Maybe they just don't think they have anything better to do. Yeah, Nina. Yeah. Okay, yeah, no team has really, so a lot of the 8s have submitted their 9th problem, and some of the 7s have submitted their 9th problem. But no one else really has, seems like they're going to move very much. Some of the 6s seem to have maybe 8. And so there could be some movement around the 6 to 8 range. But yeah, we'll see how these judgments go. We can't actually see the results because they're all frozen. But it is interesting that the queue kind of lets us know if we see something that's judging in the queue for a long time, it might be the case that it's going to be incorrect. That it's running for a long time, it might be correct, or it might be TLA or something. Yeah, it's not obvious why Rutgers is spam submitting. It seems like there's not much to accomplish there, but I don't know. It could also be a visual bug. Okay. Yeah, I don't really have much else to do or say. So yeah, well, you can just keep watching. Maybe I'll start implementing L. L looks like could be interesting to implement. So problem L, once again, was the Morse code problem. Make your own Morse code palindrome. It's a palindrome. Palindrome is a word number sequence that reads the same forwards and backwards. Palindromes ignore capitalizations, punctuation word boundaries, and we're trying to make a string such that its Morse code is a palindrome. And so one thing we can do is we can kind of do a DP where our state before scoreboard freeze, I saw a lot of double submits that were AC, so some bug then teams are multi-submitting. Yeah, it definitely could be some bug. Maybe ICPC Live knows about it. Maybe Live Team knows about it. But yeah, so the rough idea would be that at any point our DP state is going to be like a string, which is either the prefix or the suffix of our answer, and we're going to pick a character which matches on the opposite side of it. And so if the string is a palindrome, then we just immediately say, oh, the cost is 0. You don't have to add any more you don't have to add any more characters. But if the cost is not 0, then you add a character on the other side, which matches as far as it can. And then whichever is longer, like whichever has some leftover, then that becomes your new prefix or suffix. And which one is long, like depending on whether the start of the string, the initial string, or the character you added is longer, then you either get a new suffix or a new prefix that you have to like continue building inwards with. And so this is kind of just, it's just like a DP or a BFS. You can store these states. You could store these states like pretty. One thing to note is that the number of different like such states you can reach is actually very small. You could have the initial string as your prefix. You could have any suffix of the initial string as a prefix, like you could eat away a bunch of the initial string, or you can have a part of a valid Morse character as your prefix or suffix, and that there are only there aren't too many possible Morse characters, right? All Morse characters are length at most 5, right? So there's at most 32 extra states that come from like the Morse character being the prefix with suffix. And so kind of matching these up and then just treating this as a BFS is probably just a pretty straightforward way to do it. We don't really have to be super efficient with how we store states or how we manage them. We can probably just use sets of strings and just do it that way. So that's how I would probably approach this problem. And yeah, we can try implementing it because we have some time. So I'm gonna make problem. What are we calling it? L. Okay. So let's start just by inputting some characters. So car int car string p letters. And we're just going to hard code these things. So these, I think, is A and then 0, 1. We'll use 0 for dot and 1 for dash. Or maybe we'll do dot and dash. That's fine. B is dash dot dot. Dash dot dot dot. Doing this data entry is definitely pretty error prone, but I don't really know how to do it better than that, so we're just going to grind through. Dot dot dash dot. G is dash dash dot. H is dot dot dot. 4 dots. I is 2 dots. J is dot dash dash dash. K is dash dot dash. L is dot dash dot dot. M is dash dash. N is dash dot. O is dash dash dash. P is dot dash dot dash. Q is dash dash dot dash. R is dot dash dot. S is dot dot dot. T is dash. U is dash dash dot dot dash. V is dot 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 dash. W is dot dash dash. X is dash dot dot dash. Y is dash dot dash dash. Z is dash dash dot dot. And then 0 is 5 dashes. One is dot. 2 is. The counting system here is pretty, easy to follow. It's interesting that 0 takes so many. Interesting thing about Morse is that dashes take longer to transmit than dots, right? So you don't actually want all your characters to be the same number of Morse symbols. You want them to actually be the same, you want them to be like the same total transmission length. So for instance, like S takes much shorter time to transmit than O. So I don't know, that's kind of an interesting thing about Morse. And so if you're trying to optimize for speed, Morse speed, it's like a little bit different than just normal optimization. But that's fine. Okay, so so here's what we're going to do. We're going to do map int. So using state t equals pair string bool. We'll do 2 strings. So we're going to have a map, we're going to have a set state t scene q. Oh, we have to, okay, so set, okay, so map, state t, pair car, okay, so priv of Morse s equals empty string. Okay. Equals question mark. Okay. Q dot pushback. So while not Q dot empty. Okay. There are 4 and d equals 0 d. So for each distance, int z equals 4 int s equals int q dot size. IDX is less than s, IDX plus plus. Okay, now auto cur state equals q of IDX. Okay, so if first check if this is a palindrome. Okay. Bool is done equals true. Is done is done. Okay, and it's symmetric. So if is done, then okay, and then while not exit 0. Okay. Auto C per state equals priv cur state. C equals question mark, then it's bad. Break. Otherwise, cur state equals priv state. And then 0 dot empty Assert priv state of 0.empty not equal priv state of 1.empty. Values equals values. If proof state of 0 is empty, we push C to the start. Okay. Okay. If is done, count D yes. Okay. Else. Okay. Okay. Now we're done with the is done case. Now try to append. Now try to append, prepend every character. Okay, so assert. For auto CS in horse. Okay, let's rename queue size. Auto next state equals cur state. Next, if cur state 0.empty next state 0 equals s, else next state. Okay, now trim from the outside. While true, while next. If next state is 0 not equal to next dot front, 1 dot back, next is good equals false, break. Next state pop front, next state 1 dot pop back. If not is good, continue. Okay. Okay. If priv.find, priv.insert next. We try and insert it, and then if we successfully insert it, we push it in. Puts out 30QI. Is it? Here, let me. Inputs. Okay. So let's just test this. And see how it goes. But yeah, so that should be the entire solution to L. The runtime of this is, very not optimized, but the input string is only length 30, and so there really shouldn't be any nothing should really be very hard. We do have a bug, so let's really quickly debug this a little bit. What's going wrong? It seems like we're infinite looping, which shouldn't happen. Okay, here's what we did wrong. Okay. So in the first one, we did this. In the third one, we did this. Fourth one, we did this. Okay, so that seems like it works. Let's delete this print. And then also we can add some sanity checking. So for, whatever, I don't care. We could recheck Morse S plus A. But whatever. Okay, so yeah, that's L, and that should pass. It shouldn't, should be pretty safe. So yeah, back to looking at the scoreboard. We can see Cornell has more submits on H. I don't know why that would be. Maybe they have. I don't know why that would be. Maybe they have, maybe they're just trying to hide whether they got it correct. Maybe they're actually trying to pass the problem, even like they haven't actually passed the problem and they're just trying and pass it. We'll have to see how, we'll just have to wait and see, I guess. But beyond that, the scoreboard seems pretty, doesn't seem to have changed too much. There's definitely a lot more submissions now. Rutgers has submitted 9 problems, has submitted on 9 problems. SBU has submitted on 9 problems as well. Columbia has submitted on 9 problems as well. So definitely could have a lot of teams at 9, but I think it's pretty unlikely. I think we're likely to see only a handful of teams at 9. And maybe 2 teams at 10, 1 or 2 teams at 10. Yeah, it's interesting. It's not clear whether we'll see this submission on G pass. If so, it would be the only passing submission on G. And it looks like no one is attempting E, which I'm actually a little bit unsure about. As we were talking about earlier, E is a geometry problem. It's a 3D geometry problem, but it's a geometry problem that only has 6 input numbers, and then you output something, which you output something based on these 6 input numbers. And I'm pretty sure the answer is just some rational function of these input numbers. Like, I don't think you really have to solve very much to get there. Maybe you have to solve one square root or something. And so it really should be possible to have just one team member just grind out some algebra, or just sit there and think about how to do spherical geometry. Or I mean, it's not even spherical geometry, it's just 3D geometry with distances. And it seems like that would be, because you have 3 people and only 1 computer, you have you definitely have someone who has the time to do this kind of thing. And so it seems like something that could have been a good play, but no one seems to have done it. I still don't understand why this fact is true, that a sphere that passes through these 3 points also that's tangent to one of them is also tangent to the other. That doesn't. I don't see like a good reason why that should be the case, which kind of suggests that this is like a very special configuration. I don't know if. Yeah. So another way to think about it is that if you have these two spheres, right, and if you pick these two spheres that are they're like kind of homotheties away from each other from O, and then you pick the plane BAC to be a common tangent plane to both, and then you pick it to be a common tangent, and then you pick OA. You just pick OAB, OBC. Like ABC are just kind of 3 points, which they are special points because they are externally tangent. Yeah, I'm really not sure why this configuration, why this thing is tangent to all of them. It's tangent to each of S1. But yeah, that seems like an interesting theorem that I don't know if anyone has anyone knows. I don't know, Kevin, are you around? Have you heard of this thing? Do you know what this blue sphere is? But yeah, I don't know. No one seems to have even submitted it. Maybe it looked too scary, but I think it's really just some math, and it's really possible to work out. No clue, you say? 3D geometry is strange. Yeah, but isn't this like this statement is false in 2D? What is the analog of this statement in 2D? I mean, the circumcircle clearly like does not. The equivalent statement in 2D is that there's a circle which passes through A, B, and is tangent to both the in circle and the X circle. And that's false? I don't know why that would be. That doesn't feel like it should be true, especially if you have like a, well, it's not obviously false, right, Kevin? But it is false in 2D? Like, yeah, you can't really even draw a circle that like passes through BC, like AC, and like also contains the in circle and contains the X circle, right? That just doesn't seem right. Yeah. But yeah, I don't really understand how this is like why this would be coincident. Like, it's a lot of constraints. You pass through 3 points. 3 points in a sphere like already determine a thing. Already determine the point uniquely, right? Yeah, I don't know. It's pretty surprising to me. But yeah, I guess you should, yeah. I think for this problem, you just write down a bunch of formulas and then see what comes out. One thing to know is like circles touching other, like a lot of these formulas are just like quadratics. And so you can kind of just write down a bunch of quadratics and then bash. That's like pretty possible to do. But it looks like the contest is over. And so let us check in on, let's check in on the closing ceremony. See if we can see if we can find it. Oh, cool. We're in the meeting still. Okay, let's see. Okay, I will be back in a moment. Okay, looks like the opening ceremony is nearly ready, so I think we can jump into it.
All right, everybody, welcome to the closing of the 2023. Greater New York. How does everybody feel? Yeah. Before we get to the awards, we want to thank our sponsors and of course Jeff Rains and ICPC Global. Also want to thank Columbia University, all the staff and volunteers who worked this weekend. It's never easy to host a contest. There's a lot of demand and stress put on everyone here. And we should thank them for their work. So. Very special thank you, of course, to our site director, Kristen Lim. We had a lot of problems and he solved them all very, very quickly. So, almost. So sorry about the printing, but I hope we made up for it in the food this year. I hope it was a little bit better than in past years. Final thanks, of course, to the rest of our Greater New York team, John Buck, our chief judge, Fred Pickle, who's not here, Adrian Cloutey and Sevenway, who helped with operations and systems. Thank you so much. So, oh yeah, Bill, thank you. And of course, Dr. Stockhouse for coming here and grilling us today. So if we can do a quick, very quick questions, comments, and then we'll do the resolver because I think we all want to head home. So
Yes. When and where to return the USB drive?
Right here. The same thing will come around. When you get there, don't worry.
yeah, get it afterwards. Also, if anybody borrows a laptop from the university and do not return it.
There is one, somebody has one.
No, they got. So are there any other questions, comments before we start the resolving? Okay, no questions, no comments. All right, John, let's start away and John will run the resolver. Bill, I hope you do some commentary. Yeah, some color commentary.
Yeah. Sure.
Let's hear
Let's see.
You can look at the list.
Sure, let's take a look at this.
Okay, so I don't know, most of you probably have seen the resolver. Basically, what it does is during the last hour of the contest, the submissions are not posted. Your results are not posted on the scoreboard, but the judges accumulate that information. And then at the end, this program will play back the last hour of the contest in about 10 minutes. Okay.
Yeah.
And we're also going to stop when the certain awards are given out. Okay. And we're going to picture yours.
Sounds good.
All right. Let's start then. So this is what the scoreboard looked like with 1 hour left in the competition. This was the last hour. This is how now, hold on. The light green are submissions you got correct. Okay. The dark greens are first to solve. So you were the first to solve, for example, this particular problem here is the first to solve. That's the first to solve. Yellows are ones that haven't been. They were outstanding within the last hour. Reds, of course, you didn't quite get it right. So it's kind of issue. There's a red one up there. Okay? So this is what it looked like the last hour.
John, did you know that in the 70s, the contest was 6 hours? And generally, the first solution, key bunch days, right, came in after 4 hours.
But the first solution came in after 3 minutes today.
3 minutes, it's just unbelievable. And in the second half of the 70s, the worst regional contest in the history of the ICPC happened, and I had a team in it. And that's actually one of the reasons why I volunteered in that edition of the contest to, you know, to help. And hey, look, our team won. But they only solved one problem in two advance, and there was not a second team. Now, so I could postulate that you could theoretically have a worse regional contest, but only one kind of worse, right? Nobody solved anything. But what was amazing was that the challenges that we faced crafted the contests that were to come. So everything that we saw that should have been done better or should have focused on the positive resulted in change after change. So let's go ahead and find out about all these. Now I'm certainly interested in all the green stuff, but I'm quite interested in the yellow stuff.
Yeah. One other thing you should keep an eye on is anything that has a plus sign in the school name. Those teams are comprised of sophomores and freshmen only.
Wow.
Okay.
Wow.
Just so you know. There's a plus sign in the name. Wow. Right now, we're gonna jump to the end. We're gonna go all the way down to the bottom. Yeah. And so now, what's the last 1 hour? Here we go. So, gonna start resolving here. Let's see what happens. Gonna move along. There we go. So Stern had one there. No. And another one? No, sorry. Moving on. Oh. They got 3 outstanding. Let's see how they do the first one. No. Oh. Oh, no. So we didn't get Ramapo had 3. Let's come on, before that. Ramapo. Two. No. And then Cooper. And she did impact our. And see an Ann? No. Columbia bite me. One. What's that from? That last must be called. Yeah. Sorry, and then Columbia teach 10. Yeah. Count on one left there. No. That's from high. And Perot, no, they didn't get from in D. Rutgers from the carving. Oh, that's something that's. NJIT is free. Not really. Why you would get free at two? Oh, they had one outstanding. One, yeah. Only 2, 3. 1. They got. Why did binary widgets have 3? Yeah. No, sorry. NCC syntax error. No, 1964. Columbia Binding, that's in 63rd. Rutgers Hypercough was 3. Rutgers Omnicough definition in 62nd. NYU PhD is finishing 63rd. One left on. 60. Columbia team 10, 11. 11. Yeah. Two left. 7. Yeah. Philo. Oh, that's interesting. 8. Cornell Theta. Yeah. Binary 7 Cornell and U. Yeah. What's laying? Oh, wow. Cool. Okay, congratulations. That's for you. No, Princeton State. One back. No. Rutgers, Hypercar. Yeah.
So, when in computer science, earlier days, that's half a semester's work in 5 hours, right? Okay, go ahead.
Okay, Columbia team 52nd, Columbia team 11 finished 51st, Princeton team 7 finished 50, Columbia Low Lacy finished 49th, Poly 2 is 3 left. Let's see, we got here, last one. Then 48, Cornell Theta is 1 left. Yeah. No, 47. Then the silly top is 2 left. Now I'm you. 46. Columbia Literacy. I don't know. It looks like something's wrong with the software. Don't stop it.
Does anyone know what's wrong with stop with the?
I'm going to stop you. Or maybe if we press a button.
Let's press a button. We got. I think it's like the first time you said. This one to make. Yeah. I got the picture, so that we know we have 15 more minutes. I like this pressing a button. When I was young, I would press buttons, and that's why my nose isn't straight. But anyway, go ahead.
Here we go, we'll move on here. Okay, so we got all up there. And we're gonna pick up now with Cornell Edubron. We have Angus Black.
That was not. Yeah. Not mine. Yeah. Oh, there's nothing there. I think it's broken. Oh, no, it's the blitzkrieg for certain, right? You know, can we take the name? What? You know, we gave a Percocet against the world class, but then we realized actually like Lastisol is an amazing. Sorry, that team is actually still working on the problem. I think you're right on your way. It was the 32nd. I want to finish the 33rd. Rutgers. 30 in Molly 1. Lovely memory. 3. URL. Yes. 26. Highlighting again, Columbia team 2. Okay, let's take a look.
23rd, NJIPQUX. It's stuck again, Bill. Well, it's accuracy.
Okay, you go ahead.
NJIPQX team, there's some issue here. I don't know what it is. Oh, most improved. Yeah. I know you want to go, right? But I've got. Dr. Geller, Jim. Jim, Dr. Geller, come on. You don't get a medal, but you get a photo. Yeah, exactly. Dr. Geller was that site host in the back.
Ready? 1, 2, 3.
So where are we? One else data. The next one up. Let's do that. One else. Yeah. Also. Yeah. Two left. Yes, then we're gonna and then two left. The next thing is 25. Right now, we're working on study. One left. Then moving on. Another bulldog. You know, just one next two left. And the last one, no, that's 18. 30. They want me to shoot.
Yeah, they're not here anymore.
Yes. Now, then we'll go. Wow. It's not. Yeah. Oh, it's your name. Well, see you later. Thanks a lot. Still haven't signed one web. Now Unreal Analysis. You guys
So let's all sing together. The eyes of Texas are upon us. New York.
1, 2, 3.
Now we're getting down to the final six. We're starting to start dominating. We'll see. First, it takes to us one outstanding. Let's see what happens. Oh, another one. Yeah, we'll have a lot of stuff. Yeah, I think so too. Yeah. Everyone, that's you. All right, move along. Now we're really getting. Yeah. Okay, Columbia City later, they're finishing fifth, because no stop. Princeton won, they're finishing their 1 to go. Then we'll. There. Yeah. Thanks, guys. Things happen. Well, oh. Finishing third place. Being an examination. And you get the bronze medal. Ron, Hold on here. But we'll take care of that. That. And show that.
1, 2, 3.
By the way, they're also the person who solved the most problem.
Oh, wow.
They have a couple of ones here. They give me. Huh? It's another reason. That's another thing. Oh, that's another medal they got. I didn't know that. Solve most problems. And I think about first. They get another.
Come on back down.
No, that's a duel.
Well, no, that's a duel, right? So come on back down. We got another.
They got three war. They got three war. Book.
That's exactly right. Well, come on back down because we've got some more medals. Yeah, yeah.
No,
Make sure that we've got our, there we are. Okay, so if we printed the name tags, front and back, with the sheets, what would happen? It'd be in the wrong place, wouldn't it? But anyway, go ahead.
1, 2, 3.
I don't think there's any more medals. They're running out. All right, let's go. Now we have 2 teams left. I want you the second flag. By the way, at very least, teams finishing first, second, and third will be going to the NHC in Orlando. We got a gold, silver, or bronze. Going to the NHC in Orlando, and there might be more.
So, how about 4? Yeah. Okay, just blame it on me.
So whoever finished 4, that's Princeton, team 4, but we have two teams here.
So Columbia, see you later in Orlando.
Yeah, and in May,
And Princeton 1, we'll be seeing you there as well. Yeah,
And
yeah.
also, obviously, Cornell Capital will come see there.
Yeah.
Let's just see for the heck of it if they got the last problem.
Yeah. Wow. So that was yes. And of course, this particular trophy has really been a lot of places. And in a few years may have to get taller just to put the badges on there if they just want it. So congratulations, and we have one more here to bestow. There we are. Okay.
1, 2, 3.
All right. And there's our final standing, so congratulations.
Congratulations, everybody, and before we go, do you have any parting words?
Well, see you later.